In science, as important as the answers are the new and never-ending questions. It is these questions and the researchers who ask them that allow us to advance our knowledge in all fields. Questions that help us understand and tackle global challenges such as climate change. Questions that lead to the discovery of new worlds and to the development of new technologies. Ciências ULisboa is an epicenter of science of excellence. Let's learn about it together. Welcome.
Welcome, everyone. Welcome to our faculty, Ciências ULisboa. Welcome to our Ciências Research Day 2022. It's a pleasure to have you all here, where excellent science is done for an engaging and profitable session. Today, we will talk about scientific achievements, and this year's edition will have sessions dedicated to excelling, communicating, innovating, and fundamental and basic science. I would like to give you, first of all, a piece of advice. Listen to the wise considerations that will be shown between the sessions. We have invited experts from the most diverse scientific areas and ages, directly from Colégio Atlântico, and I'm sure that you will hear a bell ring in your head. So, before diving into the scientific program itself, and discover some of the most recent scientific work done here, our Dean, Professor Luís Carriço, has a message for you. Thank you.
Bom dia. Good morning. First of all, I want to greet, well, the Vice Rector is not here yet because she's providing classes. We suspended the classes here in Ciências, but we were not able to suspend the classes in Faculdade de Farmácia, so I'm sorry for that. Still, she's coming soon enough. I want to greet the representatives of the other schools of the Faculty of Sciences, of course. Our president of the Conselho de Escola, School Council, the chair of the Scientific Council, the chair of the Pedagogical Council, all members of these councils that are here. Of course, I want to greet also the coordinators of our research units. Some of them should also be greeted because they are head of departments. And of course, I want to greet the head of departments. Dear researchers, dear colleagues, dear friends, dear students, it is a great pleasure for me to open the fourth Ciências, is it the fourth? The fourth, may the fourth be with you. Oh, that's another thing, sorry. The fourth Ciências Research Day. I want to welcome you. I think you will be as amazed as I was knowing the excellent research that is done here in Ciências. Yesterday I came here to see if I had something that inspired me. I don't know if you remember last year there was a plant set up, and I used that to, in a way, make an analogy with research, because there were some plants which were very vivid and strong. Some of the other plants were very, almost dying actually, with holes in their leaves and so on and so forth. But they give me nothing. So I have to think about something else. But when I saw that, I wondered, why is not the arrangement there? Maybe all the plants died, which for an analogy with research would be a very big problem. Or they grew up and became trees, and they are very strong and are providing fruits. And I want to believe that. And I want to believe that because when I look at the research at Ciências, I see all the time better and better research. In fact, as you know, we are still the school with the best indicators in the University of Lisbon regarding the publication of scientific papers. And actually, we do it cheaper than other schools, which is also a very good thing. So within the University of Lisbon, that's a great honor. But of course, the University of Lisbon actually raised in the rankings, international rankings, where research is also a main factor. So again, research at the University of Lisbon and at the Faculty of Science is becoming better and better. So probably the plants are trees now, and there's a lot of fruits. Stand for highly cited researchers actually just came out recently, and the number of researchers that we have there also grew. So, yes, research in sciences, again, is shown to be better and better. Now, my puzzling now is about the ministry contradictions. Sorry, I have to talk about that. Why did the ministry reduce the budget for the University of Lisbon and for sciences indirectly? Because we do very good research, probably. It does not make sense. Einstein said, if we know what we are doing, perhaps we are not doing research. So maybe she turned the thing around and said, oh, they are doing very good, something that they don't know what to do. So let's take them funding. Or she just wants to give some funding to her own university or to some specific government university. Anyway, we'll never know. The truth is that we have less money. And that's one of the reasons why this year we want to recognize not only those that produce the best and the huge amount of papers and the best papers, but also those that gather the biggest amount of funding. Because funding is becoming very, very, very important in the university. We all have to consider that funding for research is very competitive, but we can get it. All of us, not just some of us. All of us, we are able to get that funding. And we have to bet on that, okay? There is no more full funding for universities. That's true with 30 years or more. You have to remember that. You have to remember that funding is paramount. We have to get funded by companies, by funding processes and programs, and that's one of the reasons that we want to emphasize the best funding champion this year. Well, they just paid me to open the session and pass the floor, so I'm going to do that. Be amazed, have a great day today, hearing the great research that we do and the great awards that we have to provide. Thank you very much. Have a nice day. Thank you.
Se tu tivesse caracol, podes pôr uma gotinha e depois o caracol fica grande.
Achas que isso que é ciência para ti? É um caracol insuflável?
Não,
então.
Podes... Há as moléculas do caracol são muito pequeninas.
Ok.
E as moléculas que tu fizeste são grandes. Então podes pôr uma gotinha pequenina e o caracol fica grande.
Boa. Já inventamos aqui uma maneira científica de fazer crescer um caracol, certo? Boa, bestial.
Thank you, Professor Luís Carriço. So let's continue with Professor Margarida Santos Reis, our Vice Dean for Research and the organizer of this event. She will present you the research highlights at Ciencias and will tell you about the Science 2021 Research Awards.
I welcome you all and thank you for being here. And I have to explain why the plants are not here. I do not speak as well as our director, but there is a reason. I didn't tell you yesterday. And the reason is they grew, of course, they are flourishing, but the reason is because we are giving the awards and people need place to be receiving the awards. So that's why there is nothing here. Okay, so I have the difficult job of trying to expose you the research highlights of a huge community that produces a lot in very different scientific areas. So as always, to think about which research highlights I should mention in this session, knowing that many will stay not mentioned here, is extremely difficult. And I apologize already to those of you that think that it should be mentioned and I couldn't. So I have some criteria that I decided. And the criteria was, first, as you noticed in the last years, we have decided to have thematic sessions. We selected a theme, and the things that were said were about this particular theme. This year, we have decided to make a program that includes fundamental and applied research. And therefore, I had also the same criteria while selecting the highlights. So presenting highlights related to fundamental research and applied research, select highlights from the different the 7 scientific areas that we have here in the faculty, selecting top papers, selecting projects. So as you can imagine, and you will see from the numbers, because I will start by giving you the numbers, you will see that it was really a hard job. I have some help from the coordinators of the centers, and I thank all of them that, in a way, just give me their opinion about the selections that I've been made. So just for those that are here for the first time, and there are always some people in the audience that are new, we have 19 research units at the faculty. So as you can imagine, it's extremely difficult to speak about all the units that we have in the faculty, but they are organized in these 7 scientific areas. So the examples I will be giving will represent the areas and selecting different research units. Let's start from the key research indicators. Our director said that we are one of the best faculties in the University of Lisbon, and this translates in the numbers that I show here. So in 2002, everything that relates to metrics relates to 2021. The examples can go to October. So we have more than 700 funded projects. We have produced more than 1,000 articles published in the peer-reviewed international journals. We'll have books, book chapters. We are very proud of having 6 European ARCI individual grants, IRCs and Marie Curie. We have more than 50 European collaborative grants, and we have increasing the protocols that we are doing. So this is really amazing. And I can announce today to everyone that we just have 2 new IRC grants in the Faculty of Sciences, one of which you will be listening in this section in the morning, which is the Maria Dornelas. We have also Inês Fragata that also was awarded with a prize from Ciência Viva in 2001 for Women in Science. She presented, because she won a prize last year, she presented her work, which was related with ARC. And we also have another person, which is Brunelov, that is in the mathematical sciences area and computational area. So he works in computational complexity. So we are very proud of having increasing the IRCs and also we also have 3 candidates, 3 submissions that passed to the 2nd phase of the interviews that will be in this November, and hopefully next year they will be speaking about their IRC grants in the faculty, and also in life science, astrophysics, and science, industry, and philosophy. As our director mentioned, we have scientists from the faculty that are listed in the world's top 2nd scientist list. So Ciências in 2021 has 18 scientists in the ranking. That is a ranking that is produced by the University of Stanford using the Elsevier databases. Last year we had 14, so we grew 4 people more in the list regarding 2021, and we hope to see this trend continuing in the next years. These are the names. What we can see here is, I cannot show the figures of everyone, the photos of everyone, But what is amazing is that you can see that it integrates all the areas, all the scientific areas of the faculty, and many of the research units that we have here. So a big thank from the direction to all of those that are in this list and that make us proud from having you in our community. And they also list the scientists that have career impact. So it's not considering their impact in the last year, but also along the last years. And again, different people from the same research units. Those in black are those that are included in the both lists, and some new names appear when we consider the last career. And also to those of you that are here and that are in this list, many thanks from us for making us so proud. But the awards are not only these. We have also been awarded by the University of Lisbon the scientific prizes. We had 4 prizes, and we have 2 honorable mentions. You know the faces here. I could put the faces because they are fewer. So we should be proud as well. And again, as you can see, we go from the earth sciences to physics to chemistry to computational and history and philosophy. How do we do this? Okay, of course, we get this because everything is based on what we produce, on the funds that we get, and as Luís said, is money that is not granted by the government, but that we have to apply for it and found it. So within these 700 projects that were ongoing on 2021, we executed, and when I speak we, is the faculty and FCID, of course, we executed almost 40 million euros. We were able to capture almost 8 million euros, and what is important here is to see that the attraction of international funds is growing. Every year we have more international funds growing, which is good because the national funds for research are decreasing. So we are in a good trend. But we also, and this should be for the next year, we should call this the Research and Innovation Day. We also have impressive indicators of innovation and entrepreneurship. So here are some numbers. I will not say all of them, but all of this work is done by Tech Labs, which is associated of the faculty, of course, is part of the faculty. And the number of startups is increasing. The investment is increasing. The turnover is increasing. We are also contracting people. So it's an amazing work, and the number of inventions, disclosures, patent applications, and protocols is also increasing. So this is really good news for the faculty, and we hope that in the future this will be in even more and more impressive numbers. So going into the advances in science and innovation, as I said, trying to give some examples from the different scientific areas. Starting from fundamental science and the mathematical sciences. In particular, here I highlight the papers and the production of one of our members, which is Teresa Faria, that publishes in very high top quality journals, and that works in something that I'm not very well, I don't know very well, but is called the Nicholson type systems. But what is important is that these systems are becoming very important in the term of applications as models for population structures in several patches or classes. And this has been very, very much used in topics such as extinction, permanence, existence, and so on and so on and so on. So it's fundamental research that is difficult to understand for those that are not mathematicians, but that applications are very useful for all the other scientific areas of the faculty. Also, and now in terms of physics, we have a huge group very well recognized, international, working on the dynamics of interfaces between active and passive systems, using basically 2 different approaches, the particle-based simulations, the continuous gross-grain models. which is also one of the research areas that you should be proud of in the faculty. Moving into the earth sciences, of course, I have to highlight this paper that was published in Nature. The researcher that published this paper was invited to present today his work, but he couldn't. He had a previous commitment, so he couldn't. But it's very important because he is the first author of a paper published in Nature, and this paper explains how a volcano can be trigger a tsunami through gravity waves, so changing the atmosphere that induces the production of the tsunami. But what we also publish in Science, another very important journal, as you know, which is one of the indicators of high quality in all the world. And in this case, we were not the first authors. But what is impressive in this work is the way that collaborative studies all around the world today can help us to understand global changes. And in this case, it was a study that was done studying how biodiversity adapts to city environments. You know that urbanization is one of the challenges of today regarding biodiversity loss. And what was studied in this case was how plants adapt to city environments. And what was demonstrated is that plants do adapt to city environments, although the processes are slightly different. But what is impressive in this paper is the amount of people that work on the paper, the amount of populations that were studied, the amount of cities that were studied, and shows us that today we are really in the global world where science profits from these collaborations that Faculty of Science is also increasing and increasing. Moving into computer science and engineering, but keeping still the cities, as you know, again, urbanization has other problems, not only biodiversity loss, but the questions related with energy and the need for an energy transition. And in this case, I highlight two projects of LASIG, one of our research centers, that are concerned with the efficiency of the energy in the buildings, and especially in creating interfaces that allows the information to be user-centered. So to have the information in real time and help the users to understand the performance of the systems that are installed in these systems. And this is also important because it joins the interests of the business, academia, and the public sector. Going into chemical sciences and technologies, here the example relates more with innovation. Innovation that is grounded in scientific research, of course. So probably those of you that were here last year saw that there was a presentation about this that spin-off from the faculty, Root and Cell, that works with, develops new medicines from the target therapy of cancers, of metastatic cancers. And this spin-off this year was awarded by the European Commission with a prize for devoted to human entrepreneurs. And so I decided it was important to use this example because it links sound research that is done in our faculty with the translation of this science into business in this case, and also contributing to the health of the population. Moving a little bit for projects. So one of the projects I would like to highlight is this Twinning for Excellence that just started in biophysics of protein interactions and self-assembly. That is a project that from the Faculty of Science is promoted by BioEasy and MARE, and it's really, again, important for several reasons. First, because of the international collaboration, but also because it addresses a very important disease, which is Alzheimer's disease, that you all know that is extremely, is a big concern for all the society as the number of Alzheimer's cases is increasing, and therefore we are very proud of being involved in this project.
moving to a different funding, and then a project that is funded by a different source, which is the PRR, that you know all, and that is funding a lot of research nowadays. I choose this example, which is adapt for grazing, which is, the objective is to adapt vegetation management using extensive grazing. So it's combining one activity that we do, which is cattle raising, and that normally produce high impacts in the systems and influences the ecosystem function. But the idea here is to manage the grazing in terms of being not so intensive and becoming more extensive, and at the same time adapt vegetation. And this will be very important for adapt the systems for the future demands related with climate change. This is also important because we have 30 partners, which are it's coordinated by the Faculty of Sciences. It has 4 higher education institutions, 3 public institutes, 3 NGOs, and especially the high number of PMEs that are related with the project. So it's a huge project. Another important project for the faculty is the nationwide surveillance system of SARS-CoV-2 and its variants in water and wastewater. This is a follow-up of a project that we presented last year with COVID-Tech, where it was a pilot project to understand how important was the wastewaters to transmit the COVID, the virus. And this project, COVID-Tech, led, together with other initiatives from other countries, led to a recommendation from the European Union that there is a need to establish a systematic system for surveillance of the virus in the wastewaters. And in Portugal, the Fundo Ambiental, together with funds from the European Community, are involved in this implementation of this recommendation, which is more or less, which involves several entities, but which I think it's worthwhile to mention, the APA and the DGS, which are important systems. Still being in the pandemic, so also again, you all know that during the pandemics, it was created the Centre de Testes da Faculdade de Ciências, and that from the Centre de Testes evolved to the AX Lab that was presented also last year. And this has been developing further and further and becoming each year more important. So nowadays, the AX Lab is a member of the Founder Consortium of an international network, RESOD, that is a network to prevent zoonotic disease emergence. But more importantly even is the participation in an international reference laboratory network, RefBio, which the aim is to strengthen the bioanalytical reference laboratories in the United Nations Secretary-General Mechanism for Research of Alleged Chemical and Biological Weapons. And related to this, we have been participating in training actions with the Laboratory for Biological Defense related with emerging biological threats. So in fact, we are really taking a leading position in this area in Portugal, not only in Lisbon, not only in the University of Lisbon, but in Portugal. And we are very proud of this work that has been coordinated by Ricardo Dias, that you all know since the creation of the Centro de Testes. And lastly, because we also have a 7th area, which is History and Philosophy of Science. Again, it's not my area. It was difficult to select the highlight, but I think it's important that we focus on another way of joining forces and joining in making synergies within our community. So I selected this IFI International Conference, which was an initiative that joined the members of the Center of History of Science and the Center of Philosophy, and addressing the same topic from both perspectives. And I think it was a successful initiative that I believe it will have follow-ups, so I think it's important to highlight also, okay? So as you see, the examples are very few. If you remember the names, 700 projects, a lot of
protocols, 1,000 publications. It was impossible to say in 15 minutes, but I hope it gives you some examples that show that we are really leading research and innovation in the University of Lisbon. Something that we decided last year, we started last year, is that we think we have so good researchers and so excellent research in the faculty that we need to give incentives to people. So we decided to create awards. And the awards are different types. The awards are prizes for individual researchers, and when I speak researchers, I'm including professors within the category, because professors are researchers, of course, and we contribute to the research of this school. And also to innovation, because innovation is a part important of our activity. So last year, as you remember, I announced that we created an internal call for exploratory projects of research. And this particular call, that can change in different years, but this particular call was to stimulate interdisciplinarity, synergies in the context of the scientific areas. So the idea was that researchers from different areas from this faculty joined together to propose projects, discuss potential collaborations, and join in projects. It was good. We have 25 project applications. These 25 project applications involved 15 research units of the 19 that we have, so it's a very good participation. And we awarded 3 projects, which I will present you immediately after this word. It was difficult to select because the quality of the projects was very high, said by the evaluation committee, and this was the decision. So the first project and I will present them not in any particular area, okay? This does not mean that this is the best than the other. It's one that was awarded. So one of the projects that was awarded was a submission by the Center of Statistics, the Institute Luís, and BioEasy. And the name is to understand how different extremes can, when joined together, can have a much bigger impact when analyzed alone. So the PI of this project is Patricia Zé Bermudez. I believe she is in the room. Can you stand up just for people to know you? And Carlos da Câmara is the co-PI. Thank you. Congratulations. So the next phase will be to do the memorandum of understanding between the faculty and the FCD and yourselves. And the projects will begin in January next year, okay? The other project that was selected is called Micro Dig Rape. So it's a larger team coming from 4 research units, BioEasy, LASIG, C3C, and the Institute Luís. And it has to do with seeking functional microbiome by assessing impact of water availability and grapevine health, physiological, etc. So the PIs of this project are Ana Margarida Fortes. I don't know if she's here. Can you stand up, please? And Francisco Couto. No sei. And lastly, but not the least, the project called Invasives. So it's about biological invasions. Again, one of the big concerns of today. And this is a project that involves the largest team, so C3C, MARE, Institute Luís, BioEasy, SESAM, and CIUCT, so different areas. And the idea is an ambitious project, which we hope it will have a major impact in giving information that can be used in decision-making, very important. So the PIs of this project are Helena Trindade, I don't know if she's here, and Paula Shein. Not all. Again, but they deserve. Okay. So I'm proud to announce that a new call will come up next year. This new call will be not about research, but about innovation. As I told you before, it's our intention to promote and to help both things. So this call will be about innovation project of exploratory character, technological innovation to bridge the gap between scientific knowledge and technology, encouraging the development and validation of a technology based on scientific knowledge. So it's a proof of concept in laboratory. We are aware that this is not a so broad interest to the sciences community, of course, but innovation is part of our work and we need to do this. So our intention is to alternate the calls, 1 year about research, another year about innovation. Again, it's also grounded in research, so it's in a way, it's also research. So the call of proposals will be open in February 2023. Be part. And Scientific Merit Awards. So last year, as you probably remember, we decided to award the research that had the highest productivity in the faculty. Considering our database, Bibelus, it's very important. The data that we use to attribute these awards are based on our database, so only those papers that are included in the reference system can be classified. And as our director said, this year we decided to move a little bit further. So we decided to give an award to the champion in attracting funding, and we decided to give merit awards also to the different scientific areas of the faculty, to the 7 difficulties. Because we know that the indicators of the areas are different. There are some areas where it's more easy to publish, other areas which is more difficult. So it's a way of recognizing that each scientific area is equally important for us in the faculty. Okay? So I will start now. In this case, we are going to attribute some diplomas. So I ask our director to come to the stage, and I ask the people that are called that come to, when I announce the names that came here, so that you can receive the award. So I will start by the Science Fundraising Award. So the champion is Tiago Capello Lourenço. Tiago, please come here. Which main research interest? The main research interest of Tiago is climate change adaptation with a focus in understanding adaptation, decision-making process, and uncertainty. This is just 2 projects, the last project that he has been working on. Tiago, do you want to say some words? Yes?
Thank you. Well, first, sorry for the plant. I didn't want to be the reason for not having plants here. Well, first I would like to thank the Dean, Professor Luís Carriço, and Professor Margarida Santos Reis for the award, but also, and all the board of Ciências, of course, but also the teams at Ciências ID, because without Ciências ID, I wouldn't be able to attract the funding and to do my work. Obviously, getting funded in science is a hard task. You are all aware of this. It takes time. It takes support from others. So I would also like to thank everybody who has worked and works with me in the different projects, and also my colleagues at CFTC, and obviously eChanges for the good discussions and pushing me forward. And the next steps, obviously, is to turn the funding into proper science, and to get more publications, and to get even more projects, and also to support younger generations of researchers and students, and doing all this at the same time. You all know it's not easy, of course, so it's the next big challenge. And so maybe, already losing my diploma. So maybe next year I can be on the other.
You are competing for the next award.
Yeah, for the next award on the publication. So thank you very much. Obrigado.
Thank you.
Thank you it's an honor.
Thank you very much. So no, figures. So now I'm going to announce the merit awards for scientific area. I will call all in a row, so I ask all of you to come here. Unfortunately, we will not have time to give you the words, so just a clap of hands, okay? Because of time constraints, just that. So I will start with no particular order. It doesn't mean that it's the best one. It's just one order that I select just for, I think it's alphabetical. So I start with the chemical sciences and technologies, and I call Professor Margarida do Amaral to the stand. The next one is computer science and engineer. The winner was Tiago Guerreiro. He's not here, Tiago Guerreiro. But the prize will be received by his PhD student, Diogo Branco. Please, Diogo, come to the stage. Earth Sciences, Pedro Soares, Matos Soares. History and Philosophy of Science, Ana Duarte Rodrigues. Life Science, José Pedro Granadeiro. And Mathematical Sciences, James Kennedy. You can stay over there to take the photo. You stay there with them. So, many thanks to all of you for contributing to the excellent science we do in Ciências. Thank you very much. Thank you. Agora faltou o Tiago. Não sei se queres. Pronto, está bem. Nada, estava a dizer. So as you probably noticed, there is an area missing here. There were 7, there are 6. So we still have one area that I didn't call, and it's not because they didn't deserve the award, but because this area and the researchers of this area received, again, this year, the award of the best science productivity of Ciências as a whole. So I call Francisco Lobo again to the stage. Thank you very much. Thank you very much. So with this, yeah? Também queres umas palavras? Não, ele vai falar a seguir. Ele vai ter mais tempo. So with this, I finalize the presentation. Sim, sim. Thank you very much, Mr. Director. So this is thus. I hope I have shown a little bit of what we have done in the last year. We are driven by excellence, and this time I quoted by Laziz because I was already called the attention that this is copyright from Laziz, but I think it applies to all the faculty. I'm sorry, but I said, quoting Laziz. So thanks for listening, and now it's time to give the word to the awardee, to Francisco Lobo, so we'll have a little bit more time. But before that, I wish to thank these persons that make this event possible. Thank you very much.
So I'm surprised, thank you, Professor. So let's continue with Professor Francisco Lobo and his presentation. Thank you, and congratulations.
So thank you very much once again for the direction of the science faculty of the University of Lisbon. I feel very honored, and it was a surprise the second time, but thank you very, very much. Thank you very much. It means a lot because I'm ex-student of the university, of the science faculty, so it means a lot to me. So thank you once again very much. Okay, so like was mentioned, I think I'm a researcher at the Institute of Astrophysics and Space Sciences, and I'm going to speak today about, let me just see how this works. Okay, so I'm going to speak about a different topic than last year. So I'm going to speak about these two topics, black hole physics and gravitational waves. So my research is basically in these three topics. In cosmology, I do most of my research in modified theories of gravity. We do a lot of research with all these modifications of Einstein's theory, which I spoke about last year. But this year, I'm going to focus on recent developments, recent discoveries on black holes and also gravitational waves, which are extremely fascinating physics. And black holes are really a test bed for all these theories, especially also quantum mechanics. There's a lot of research coming out recently, especially for the Nobel Prize of this year, which was related to entanglement. Okay, I won't speak much about it, but black holes is also a test bed to test these entanglement states that are very, very important in quantum mechanics. Okay, so I told Margarida I'll be quite fast, so I'm going to be quite fast. So I'm going to present an equation to you. Don't be frightened. It's one of the most famous equations of physics. It's the Einstein field equation, okay? So I'll just give you a very brief outline of what it is, and then because all that I'm going to speak about is related to this equation. So over here we have this quantity. It's a quantity that's related to geometry. It's called the Einstein tensor. So in this part over here, this T is the distribution of the energy momentum tensor, okay? So here's an equality between two different things, okay? Matter and geometry. So you may wonder what is the relationship, and it's very profound because I'll give you a very brief outline. So this, in terms of the dynamics, tells you that it's this part, the distribution of the energy momentum tensor, that distorts geometry. Okay, and it's this distortion of geometry tells matter how to move. So that's the dynamics of this equation. So basically, that's what happens here. I'll just play the video once again. So the sun has matter. It distorts space-time around, okay? And this space-time curvature is felt by the Earth, and the Earth moves around the sun. It's this gravitational interaction. So there's no instantaneous gravitational force a la Newton here. So the gravitational interaction is due to the space-time curvature. So it's really important here. So this tells you that in Einstein's theory, okay, space and time are really relative. They're not absolute quantities like in Newton. So here one can stretch and compress and ripple space-time. It's these ripples of the fabric of space-time which are the gravitational waves, okay? So if you can stretch space-time, and if you can stretch it to some extreme, one can also rip it, okay? And therefore one gets these very exotic objects, which are the black holes, okay? So I'm going to speak to you a bit about this. So this was the object of the Nobel Prize in 2020. This is a diagram by one of the laureates of the Nobel Prize on black holes. So essentially, there's a natural mechanism for the formation of these black holes. So if you have a massive star, and when it collapses, okay, so which is represented over here, so here's the matter that collapses. It's got a mass of about 5 times more than the mass of the sun. It collapses and it enters in this very strange surface form that's called the event horizon, which is denoted by this part over here, okay? And then as matter goes into the center, it forms a singularity, which one can consider as the ripping of space-time, okay? So here, space-time rips, and that's a test bed for quantum gravity theories, which is very important, okay? So, but what is important is that there's a time over here, okay? A time, so this, here is time. So there's a certain instance where this black hole is formed. So a black hole is a purely gravitational object. It's a vacuum object because all the matter that formed this quantity is really destroyed in the singularity, okay? So that tells you that if you want to solve your Einstein field equation, so what you do is just consider vacuum, okay? This over here is 0, and then you solve the Einstein field equations, which are 10 coupled second-order differential partial equations for the mathematics, for the mathematicians, sorry. So this here is, it's an index which goes from 0 to 3. So in fact, there's 16 equations here, and then due to the symmetries, you have 10 equations. And then also due to specific symmetries, one can reduce your system. But the simplest solution is when you consider vacuum. So when Einstein proposed this equation back in 1915 in November, he said these equations are too difficult to be solved. A few months later, they were solved. They were solved by this mathematician that was in the Russian front, and his name was Karl Schwarzschild, okay? So that's the famous Schwarzschild solution, which I present here, okay? And nowadays, it's what we call the static and spheric symmetric black hole solution, okay? This is a Penrose diagram of that gentleman that received the Nobel Prize in 2020. So a black hole is a local object, and it goes out into infinities, right? So it's an infinite object, but if you do some transformations, and it took about 50 years to really understand the solution. And only in the late 50s, early 60s, that they really understand this, the solution with Penrose and also other gentlemen. But this Penrose diagram here brings in infinity, okay? So you have all the space-time in this finite image. This here is our universe. This is the so-called event horizon, which is tells you when R is equal to 2m, when G and C is 1, so that's the event horizon. Any object that goes into the black hole stays there, okay? And then all the matter is destroyed in this singularity. And the Schwarzschild solution is extremely rich. It tells you that you have this solution, the interior of a black hole. You have our universe, you have a white hole, which is a kind of an anti-black hole, and you have this very strange bridge. It's the Einstein-Rosen bridge, okay? I think most of you have heard about this in the science fiction films. It's a non-traversable wormhole, okay? Where people traverse, but it's not traversable. And it also has a solution of a parallel universe, okay? So this is just the basic background for you to understand what's coming next, okay? So last year, and in the last couple of years, we've been working a lot with very novel solutions, and we found some regular black hole solutions. So taking into account the so-called Penrose diagram, so over here, it's quite complicated, but instead of this singularity, we have a bounce. So this black hole solution, as it collapses, it bounces up into another universe, okay? So we have here, in fact, our universe. So our universe is a kind of a cyclic, it's got a cyclic behavior. And there's also different solutions that one can take into account. So one can also have bounces into other universes. So there's a kind of a multi-universe here, okay? So these solutions are really important because they're regular, that, in terms that they singularity-free. There's no singularity. So it's important in the sense, okay? So we have another 4 or 5 papers with this, and it's been highly cited in the last couple of years. So recently, I'm sure that most of you have seen these 2 images, okay? It's images of a supermassive black hole. So that Schwarzschild black hole is a paradigmatic astrophysical black hole. Okay, it's small, but these supermassive black holes that were shown, the images, this is our black hole at the center of our galaxy. This is the black hole in the center of a very distant galaxy called M87. And these have enormous masses. So our one has about 4 million times the mass of our sun. So it fits into the orbit of Mercury. It's really, really huge. It's rotating quite fast. This was announced this year in April. This image was announced in 2019, I think, about 3 years ago. And it's really huge. It's got about 6,000 million times the mass of our sun. It's enormous, okay? So our solar system fits into this little tiny region. But if you see, the structure is very similar. One has this so-called black hole shadow. this dark interior, and there's also some rings over here. But this over here is the accretion disk. So one cannot really see a black hole. What one sees is the matter that's falling into the black hole, okay? It's the so-called accretion disks, okay? So these images over here are the images of the accretion disks, okay? And so let me show you how this works. Here's a black hole, for instance. We have here a plate where you see the image. So this over here is the so-called black hole shadow. So here's the accretion disk, and we've seen the accretion disk from the side, okay? So light rays coming from here, hit here, and one sees this, this disk, and light rays coming from the back of the black hole, as space-time is curve, and one sees a kind of an arc on top and at the bottom. But the image also depends on the way that you look at it. It depends on your perspective. So if you see an image from top, what you see is this thing over here. And note that there was this ring. It's the so-called photon ring, which one can also discriminate several black hole solutions and also in different modified theories of gravity models, okay? So it's quite important. Quite curious, about 12 years ago, we had a lot of work in thin accretion disks, which has been cited quite a lot. So I just want to focus this because it was great to see all this work being cited recently due to these images. So recently, we had 3 papers that came out quite recently. We have another 8 or 9 already submitted. But these papers also try to discriminate different astrophysical objects. So it may not be a black hole, okay? It might be something else that we don't know, or some kind of black hole, or different from the Schwarzschild black hole. The Schwarzschild black hole is a static solution. We have the Kerr solution, which rotates, so that is the most realistic one. So we also have many, many variants of these black hole solutions, and it's important to try to discriminate these objects, okay? So there's observational signatures that one can take into account. Gravitational waves. So this is what is revolutionizing now modern science and modern astrophysics. So what are gravitational waves? So we saw that space-time is curved. It can also ripple. And how can one detect these ripples? So if you have black holes orbiting, which are vacuum solutions of the Einstein field equations, and orbit around one another, so this orbiting ripples space-time in such a way that it emits these gravitational waves, which is this purplish part here. And what we measure on Earth in the LIGO collaboration is this wave. So you see that as the black holes orbit faster and faster, space-time curvature is much higher, and we're going to stop the video when both black holes fuse together, and we have this peak here, okay? So this peak is when both black holes fuse, okay? The space-time curvature is very high, and one black hole is formed, and it's spheroid. So it starts oscillating, as one can see over here, and one can see this kind of a ring-down signal. And what we have is an enormous amount of gravitational energy that's emitted in the form of gravitational waves. So the first detection was in 2015, 14th of September. They received the Nobel Prize 2 years later. And well, to give you an idea, one black hole had about 29 masses of the sun, the other one had about 34, 35, and the sum was 61. So 4 masses of the sun was emitted as gravitational waves, an enormous amount in a very, very small time. So LIGO just detects these gravitational waves in the last 7 or 8 orbits, okay? Let me just go forward. So LIGO, which I didn't speak about, is a project which detects these gravitational waves. There's been 3 observational runs. To the moment, we have about 90 observations, which are fantastic. We have different combinations. We have the collision of 2 black holes. We have collisions of neutron stars and black holes. We have collisions of neutron stars, okay? So note that if you have the collision of 2 black holes, what you have is the non-emission of electromagnetic radiation, because these objects are purely gravitational. What they emit is just gravitational waves. If you have now neutron stars, which have a huge density, they also emit electromagnetic waves, gamma rays, X-rays, and all that. So these are the detections that we're really looking for. And there was one in 2018 which was fantastic, and it's rewriting all the textbooks. So we have now at this moment, we have 90 observations, 90 confirmed candidates. LIGO will switch on again in December, and it's been predicted to see a few gravitational events, a few gravitational collisions, you know, per day. So it's very, very sensitive. So now at this moment we have four observatories. We have the two in the United States, we have Virgo in Italy, we have Kagra in Japan, here we are, and LIGO India has been really delayed due to political issues, but hopefully it'll switch on in 2025 to 2026. So the more observatories we have, the more one can localize the source and really say much more about the sources. So I'm going to move forward. Very important is this one, LISA, which the science faculty is heavily involved in. It's the space-bound, it's a space type LIGO observatory in space. So it's got about the dimensions is about 2.5 million kilometers. So this is an extraordinary technological feat. And it'll be so sensitive that it can measure all that LIGO is measuring. It's so sensitive that it can measure the gravitational waves coming from the Big Bang. We can see the Big Bang for the first time, literally. It's so sensitive that it can see the signal of any collision weeks before it collides, and it can tell the observatories on Earth, look at that point in space that there will be some event there, and it might be the collision of two neutron stars. So there's a lot of science involved. Let me just say that the IA has about 15 members involved in this consortium. About 12 of them are from the science faculty. And we had quite a few papers that were related to this collaboration. So let's just step back and see what we have here, okay? So since, I will end now, just 2 minutes. So since forever, we've been observing the universe through the electromagnetic radiation signal, right? Everything we see is through light, right? Or electromagnetic radiation. Since the revolutionary act of Galileo in the 16th century, when he pointed his telescope, his luneta, right, to the stars, and he discovered so much stuff that, well, the moon had structure, he discovered the 4 moons of Jupiter and a lot more. So over the years, we've been observing the universe through the electromagnetic spectra, okay? Through gamma rays all the way to microwave, all the way to radio waves, okay? For the first time, we're observing the universe through the gravitational waves, the dark side, the warped side of gravity. So we also, here in this revolutionary act of pointing our telescope, our gravitational telescope, which is LIGO, and we're discovering a lot of new stuff, okay? And also, LISA, there's also new techniques that are involved. And let me say that it's also extremely important to be involved in these missions, okay? So the IA, the Institute of Astrophysics and Space Sciences, is very involved in the ESO and the ESA missions. We have a lot of missions that we're involved in, co-leadership. We're leaders in many work packages, and there's a lot of important ones. Let me just focus on this one, Euclid, which the researchers from the science faculty were involved in the mapping, the survey of the sky. So very important, and let's hope that we continue with these people, because the human resources are lacking. And the Euclids had a great setback because the launcher, which was a Russian launcher, refused this year to launch the spaceship, but they reached an agreement with SpaceX. So hopefully in the 3rd quarter of next year, the Euclid will fly. It will send data which we can analyze by the end of 2023. There's also a lot of synergy between missions, LISA and Athena. Athena, we have the co-PI is from the science faculty, it's José Afonso. So he's the co-PI of this mission, this project, Athena, which will measure X-rays. This will be really fantastic, if LISA will detect some gravitational wave signal, it can tell all the observatories, especially Athena, to point to that point of the sky, and they can really measure precisely all the gamma rays and the X-rays that come from that localized source. So there's a lot of synergy between all these missions. And so these are missions related to ESA. We also have a lot of missions with ESO, the European Southern Observatory. I wish I had time to speak about each one of them, but I don't have time. But I will leave this one, Moons, which was the instrument. Moons was built here at the Science Faculty of the University of Lisbon, and we'll be hearing about it at 12 o'clock by Alexandre. And as we speak, this instrument is being mounted, so he will speak about more about Moons. And also the co-leadership of this, the co-PI of this mission is also from the Science Faculty of the University. Just to say, it's extremely important for institutes, centers to be involved in these missions. And we thank extremely the direction of the Science Faculty and the Science Faculty of the University of Lisbon for being a mothership and harboring all these missions, which are extremely important for international science and to give the Institute and the Science Faculty all the visibility due to these missions. And so let me just say that, so a very exciting and busy time ahead. Thank you very much.
A ciência para mim é uma área em que, por exemplo, testam coisas, por exemplo, conseguem saber o que é que se passa, como é que irão curar, como é que irão fazer e desenvolver coisas para melhorar o mundo.
So let's continue. Again, with our Vice Dean, Professor Margarida Santos Reis, let's start with session 1, Excelling.
Hello again. So the first speaker for this session will be Vladimir Konotop. If you paid attention, thank you, Vladimir. If you paid attention to my presentation, you will probably notice that Vladimir is one of the scientists in the top 2 of the ranking, both in terms of career impact and in 2021. He works, I believe I'm saying, well, theoretical physics, more specifically optics. And so I give you the floor. Thank you.
Again, thank you very much for the invitation. My talk will be about non-conventional steering of light. Here I mean steering which considers such phenomenon as incommensurability, topology, and nonlinearity. So just in the previous talk, we learned how light is important for our life. And so life served people since ancient time, and while climbing this rock of knowledge, people learn about light almost everything, understand it in quantum and classical level, and elaborated quite sophisticated ways of producing and manipulating light. These methods, these technologies were moved already from scientific labs to engineers, to manufacturers, and I would call them as a conventional method. At the same time, in the last few years, we also observed a fantastic explosion of new technologies in material sciences. And in particular, now it is possible to design practically any optical media at will. Very soon physicists understood, working with optics understood that this means that designing right optical media, one can make light to simulate other phenomena in other areas. So light becomes a simulator. Moreover, when this is done, this opens a new possibilities for manipulating light. And these new possibilities for manipulating light I call non-conventional, which emerged in the last maybe 10 years. So I will be talking about my participation in 4 experiments about linear localization of light, and non-linear localization, which is called solitons, which is achieved in photonic MARE lattices. Then I will tell you a few words about the experiments where nonlinearity was used to introduce topology in optical media. And finally, very recent results about quantized transport of light. So speaking about photonic MARE lattices, we mean, first of all, two or more lattices superimposed one over another. So here and here we have examples of honeycomb lattices, rectangular or Pythagorean lattices and honeycomb lattices, which are, these are geometry of these lattices, and these are experimental images of these lattices. And what is about this lattice special is that depending on the angle of rotation, these lattices can preserve periodicity or lose it. And then when they preserve periodicity, we call it as a commensurate phase, or when they don't preserve commensurability, we call it incommensurate phase. In the second case, the translational invariance is broken. So these blue rays show commensurate phases, and these are incommensurate phases, okay? When translation invariance is broken, then one can think about the following. So what would be if one passes light through this medium? So here are two examples. One is actually quite obvious, which is this one. So if it is a commensurate phase, then the light will spread out, and this is what physicists very well known as a block wave on the output of the system. However, when the lattice is in non-commensurate phase, so the lattice does not spread. It remains localized even the medium is linear. So there is no any other physical mechanism except broken symmetry that makes light localized. So these were our numerical simulation, and then if one try to scan angles, considering different angles, in optics, these different angles can be easily, relatively easily imprinted in the photorefractive crystals. We, not we, but our friends in Shanghai went to the laboratory to set up experiment, which was based, which used a photorefractive crystal, for which we several light beams imprinted the lattice, which you can see here, and one light beam was used in order to as a probe beam, which was either localized or delocalized at the output. So the result is shown here, and you see this from the top to down. It's when one of the lattice is always on, another starts increase the intensity, and we observe that in the commensurate phase, we always have the localization as expected, but in the incommensurate phase, we have very nice localization. This was published in the Nature 2 years ago. Now, in optics, unlike, for example, like most of the systems on condensed matter, can easily put in the system nonlinearity. And then, this is what I wanted also to show, is that these are results for Pythagorean lattice, but the same result one can observe to the honeycomb lattice. So that means that this is a general phenomenon. So when optics allows to put nonlinearity in the system, and if we consider the same two types of the lattice, MARE lattices, I could not avoid write an equation here because I'm theoretician. So we get here additionally a nonlinear term, and when we start to simulate this phenomenon, we observe actually, in the commensurate phase, we observe two well-known phenomena. One phenomena is that in order, even we have nonlinearity, nonlinearity by itself can localize light, but this localization of light is achieved only if the intensity is high enough, so above some threshold. And you see here this threshold, these lines. So about this threshold, we have this localization. If we are below threshold, then localization is impossible, and we are we see again two-dimensional block wave. In this case, localization is called 2D soliton. The problem of 2D soliton in optics is also that it could be highly unstable. Actually, in homogeneous wave, it's absolutely unstable. So it's not useful practically. So what we thought that using the MARE lattices in incommensurate phase, we can resolve two problems. First, we can eliminate this threshold, and second, we can stabilize this pulse. This is what we observed also numerically. So after that, again, we went to the laboratory. This experiment was, of course, cheaper because everything was done. We only needed to increase the nonlinearity, intensity of the light. This was done. And here we see scanning over theoretical and experimental results of scanning over angle. And we see that for the threshold intensity for exciting localized light, here we have some non-zero threshold, but when we are in commensurate phase, we are practically at zero level. And here theoretical and experimental results are perfectly matched. And this is the real experiment. These are experimental images showing how this behaves when we input light at low intensity, high intensity, low intensity, high intensity, but with in the commensurate and incommensurate phases. Well, after that, that was published in Nature Photonics. Another next problem which I wanted to mention here, or experiment where I was also work in which I was also involved, is a nonlinearity induced to photonic nonlinearity induced photonic topological insulator. What is this? So imagine that we have an array of waveguides. These are imprinted waveguides in this matrix. And then these are nonlinear medium. And then what happens is the following, that these waveguides are connected with each other through the couplers. And then what happens is the following, that if intensity is very weak, then light spreads out, it diffracts. If we start to increase nonlinearity, then we start then we expect to observing traveling of the light along the boundary of this system. This is a very well. This is an analog of the very well known in condensed matter physics phenomenon, which is called quantum Hall effect. Except that now the topology here will be introduced by the nonlinearity. More specifically, when one considers a coupler, which is a small element of this array, one can see that for low intensities, this coupler is topologically trivial. It is equivalent, it is topologically trivial to the sphere. But if we increase the nonlinearity, then appears non-trivial topology, which is more equivalent topology of the torus, which is here. Why topology is important and interesting? Because topology is a global property of the system, not the local one. And this means that if system topological, then local imperfectness of the systems are irrelevant. So light will not fill them. They will go through the through the path we designed for it without any distortion, reflection, etc. So this is, then we put this in computer. This is an equation, and this is the experiment, the result of the experiment, where indeed these circles are the output waveguides, and we see what happens at low intensities, which are shown here, and at high intensities, which are shown here. So at high intensities, we have a kind of current of light through the surface of this structure, while at low intensities, we have dispersion. So this was published in Science a couple of years ago. So finally, our very recent results, which were obtained indeed very recently. So that in nearly 40 years ago, Thouless discovered one thing, that if you have a periodic potential, periodic in space, and we also modulate it periodically in time, then we can obtain a current. And this current will be topological. So it will not depend on the velocity of modulation. After one period, independently on how is velocity at one period of modulation, the output will be the same. So Thouless did it for electrons in one-dimensional crystal. So we thought that our MARE lattice would allow us to see this, but in two-dimensional setting and with light. More specifically, now, unlike in the previous result, we have still two lattices rotated, one with respect to another, but then we have also some tilt angle. And this tilt angle, makes the following, that when we follow light along this crystal, the light see the breathing potential, or optical potential. And putting this in the computer, here are the results, theoretical and experimental. So these are lattices, the experimental images of the lattices. This again was done in the lab in Phase Lab in Shanghai. These are theoretical predictions, and these are experimental observations. As a matter of fact, this observation match is extremely good, especially if we put this line below, forgetting about this delay time, and taking into account that this is what is called adiabatic effect. It is very relevant that everything happens very slowly, because if it starts going very fast, I mean modulation of the potential. If it becomes fast, then new effects are coming into the play. So this is equation describing this system, and this pumping is described by this additional term. This is still a linear pumping, and this you see the results of the experiment, where we follow the center of mass of the light. And this means that, center of the beam. And what we have this beam on the input, and then depending on the, I think this is one period of oscillation, we have exactly shift one discrete interval here, and then another, after second period, we have shift the second discrete period here. This is, this should appear still this year. Finally, these are results I wanted to show you. As to outlook, there are plenty, because theory practically not done yet, in the sense that we have qualitative theory, not really theory. And we can, especially for non-trivial topology introduced by nonlinearity, then we can add, and these experiments are already in the process, add nonlinearity for two-dimensional pumping and study two-dimensional Thouless pumping of the light. By the way, that was the first study of really two-dimensional pumping of the light. And finally, not finally, this one of the next possibilities is to apply everything to atomic systems in periodic potentials, exploring mathematical analogies. How we do this, I don't know, but we heard the phrase of the Einstein today that if I would know, that wouldn't be a science. So probably this way. And of course, to finish, I should thank all people, collaboration with whom I enjoyed a lot, and collaboration with whom lead to this result. And we're still collaborating, and I hope to have new results to show soon. And of course, thank you for your attention today.
Thank you very much, Vladimir. So we move to the second presentation, which is from Maria Dornelas. As I explained in my presentation, Maria just won an IRC grant, and she is a former student of the faculty. She done biology here in the faculty. Then she moved abroad and now is working, or was working and is still for a moment working in St. Andrews University, but decided to return to Portugal. So she will going to speak to us about the grant that she received and the project that she will be developing in the next years in the faculty. Thank you very much.
Okay, thank you very much. Good morning, everyone. I want to start by just taking a moment and to say it feels amazing to be standing in the lecture theatre where I did my undergrad. And to say a big thank you to everyone who taught me and sort of shaped me as a scientist. I've been away for 20 years, but it feels great to come home. So the brief I got from Professora Margarida dos Santos Ferreira was to talk about the project that we're starting here. And so this is going to be a presentation that's a bit light on results, and it's going to be a little bit arm-wavy, and these are the approaches that we're taking. We don't really know what we're doing, or we wouldn't be called research, right? I mean, the topic of this project is linking environment, species composition, and function on coral reefs. So, you know, seeing as coral reefs are the ecosystem that the project is focused on, I figured we could start this talk by me taking you to probably my favorite reef on the world. This is a reef we call Trimodal, where I've been going since the start of my PhD. This is a photo taken at the start of my PhD. And it looks pretty cool, although we had scared all the fish away by the time we took this photo by spending hours and hours and hours with our head in the coral. But this is how the same reef looked after a series of 2 Category 4 cyclones and 2 massive heat waves wiped out 98% of the corals that lived there. So this is a photo that was taken in 2016, and at this time, one of my PhD students, she's here, Viviana, she's going to be part of this project, was starting. And I couldn't really find any corals on the reef, so I could teach her coral ID. So this is, like, for me personally, extremely sad, because it's a place that's very close to my heart. It's a place that I've studied for a long time. I've spent, I don't know how many hours with my head in the middle of this reef. But it's not just this reef, right? So it's something that is affecting coral reefs around the world. And this is problematic because coral reefs are extremely high concentrations of biodiversity. About a third of known marine species can be found on these ecosystems, although they occupy less than 1% of the oceans. They're also really important for us, for people. About 500 million people rely on coral reefs for their subsistence in all sorts of different ways. So actually figuring out what's going to happen to coral reefs is important as well as general. So work that I've been involved in, both sort of coming out of my lab, but also with collaborators, has been showing that we see like strong signals of widespread biodiversity change across the planet. And we know that species composition in particular is changing everywhere, and it's changing fast, faster than the theoretical models that we can come up with can predict. We also see evidence that the pace of change is accelerating, but it's a complicated change in that it is actually, there's sort of winners and losers as part of this change. We know that there is important geographic variation in biodiversity change at the moment, with the marine realm, and in particular the tropics, seeing among the fastest rates of change. We can find some drivers of this change, the forest loss and climate change among them. So we know it's a fast changing planet. We know the environment is changing. We know species composition is changing. In an interview I gave last year, I describe this as species playing musical chairs. So we see like the music is playing and then it stops, and then we figure out that we have different species in different places. And all of this begs the question, what are the implications of all of this change for ecosystem function? And evidently, humans rely on ecosystems for all kinds of things. So this is like the big topic that this project is aiming to tackle, and we're hoping to tackle it from a theoretical and an empirical approach. So starting with a little bit of ecological theory, and I hope that the people who taught me ecology are in the room. I won't be, we'll be happy with this. So we can borrow three forms of the concept of niche in ecology to help us understand these links. So the first one is the Dornelian niche, which is basically what a species needs, so the environmental conditions where it can survive. The second niche concept that we're going to borrow is the Eltonian niche, which is what a species does, how it functions. And the third niche concept is a little bit more recent and actually comes from evolution, not so much ecology. And it's the concept of niche construction. And basically what this is how a species' function alters the environment around it. So we heard about light in the previous talk. So one of the things that corals do is they change the light environment around them, and then this has consequences for the corals that live there. And so the plan for this project is to study these three niche concepts and how they are linked as part of a feedback loop. So we know that the environmental conditions, the species compositions environment affects the species that can live there, and through the Dornelian niche. We know that the species that live in any particular place function in particular ways. They grow in different shapes. And we know that function then affects the environment, and that's the niche construction. And so this creates a feedback loop that we plan to study. And so here's a little animation, arm wavy, how exactly we plan to tackle this. Let's imagine an environmental gradient. It could be light or temperature, for example. And we'll have our focal species here, and this species is going to have particular conditions under which it can and cannot survive, and they're optimal conditions. And this species is going to also have functional rates, right? So the rates at which for example, if it's a coral, the rates at which it produces rock, because corals are glorified slimy rock, it's what they are. And then, depending on the shape of the coral, it's going to alter the environment around it in different ways. So by sorting species along these different niche axes, we can start to look at the relationship between niche construction, the Eltonian niche, and the Dornelian niche. And we did this by looking at bivariate distributions. So it is possible that, for this particular example, we'll have the positive covariance in terms of the distribution of the species along the Dornelian and the Eltonian niche. And so this means that we can map effects of the change in one niche axis for the other niche axis. So for example, if we have an assemblage under certain environmental conditions, there will be a number of species that can survive under those conditions. So those are the species that intercept the yellow line that is marking where in the environment we are. And then we can estimate what are the functional rates that we expect for the species that we have present. And if the environment changes, that is going to potentially alter the species that can live there. And we can then map what are the implications in terms of functional rate. So that's the theory. We're going to attempt to link these three things. We're going to develop the theory that links these three things, but I'm going to borrow someone else's words. Theory without data are ghosts, and data without theory are corpses. And so the plan of this project is to actually develop both things at the same time, and we're kind of in a good place in that we can harness technology to help us collect environmental, compositional, and functional data really, really efficiently, and that's what we plan to do. And this slide, I don't know what happened here. Okay, so we have been, oh, I know. I'm missing a video, I'm really sorry. I wanted to show you the maps that we do on the water, but somehow it didn't quite work. So we've been mapping corals on a reef for a number of years now. We do maps the size of football pitches with less than millimeter resolution, and then we spend many, many, many hours with our heads in the coral trying to identify all the corals that live there. And so we plan to use these tools to very, very tightly connect environment, composition, and function. We have this long-term study site at Lizard Island, where I'm going in 2 weeks, that we're going to continue to visit, but we plan to expand our study sites so that we end up with 100 sites in total. Our estimate, we're currently keeping track of about 30,000, like 29,000, right, really, but I suspect in a couple of weeks it's going to be 30,000 coral colonies. We plan to expand that to 100,000. By the time we combine the data that we're going to collect with the data we have in hand, it will be over 10 years of monitoring. So the big advantage of monitoring things through time is that you can actually measure change, and that's what we're going to do here. In terms of the environment, we're going to keep track of the physical environment, so reef structure that we extract from our maps. And we've been developing geometric theory that allows us to quantify the shapes of corals in useful ways. And we're also going to be deploying lots of data loggers to keep track of temperature, flow, and light. And we're going to have focal coral colonies as well, so that we have sort of a nested design that allows us to, in some particular places, go at really, really even higher resolution. In terms of function, we're going to, because we're going to measure these things through time, we can measure growth. We can measure reef accretion and erosion by comparing digital elevation models in our maps from year to year. And we're going to keep track also of settlement of baby corals, as well as fecundity. And by doing all of these at the same time, we will be equipped to not just develop theory, but to have the data that we're collecting guide the theory that we have in the end. And that's it from me.
Thanks, Maria. We are looking for results, and this project will be a huge opportunity for students that are in this room that may be part of Maria's team soon, and that could go to these corals, diving and looking at the corals, which I would like to go to. So for the last presentation before the coffee break, Professora Margarida do Amaral. So Margarida, as you saw, is also in the top 22 scientists in the rankings, and also just won the prize for the 2000 Best Productivity of the of the area of chemical sciences. So we move now connected with health.
Thank you very much for the introduction. I want to greet, of course, the Board of Directors for the prize, the award I've just received. I was actually looking for the check. I didn't see it, but that's okay. Of course, Vice Rector, Professora Cecília Rodrigues, it's a great pleasure to have you here at the university. I'd like to, first of all, thank my team, because I got the award, but they've done the work, so I don't know whether they are here. But of course, research these days is teamwork, and I very much like to acknowledge their work. At the end, I'll show you their faces. So I'm not showing any equations. I'm not showing any nice photos from corals in Australia, but I'm going to shift gears here and talk to you about disease and how to treat, in this case, cystic fibrosis, which is a rare monogenic disease. So today's great biomedical challenge is treating patients more precisely and effectively in ways that better meet their individual needs. And that's what we call personalized or precision medicine. So let me show you with how this works. If we have a group of patients in the classical therapies approaches, we have the concept of one drug fits all. This means that a group of patients, actually the largest group of patients in trials, will get benefit. However, some individuals will not get benefit, and some other group, usually smaller, will even have adverse effects. If we use the approach of personalized medicine, we need to have some distinctive biomarker which allows us to give the right drug to the right person so that every individual actually gets benefit. So, what this child is doing here, actually this goes at top speed. How do I go back? Yeah. So, what her mother is doing here is a form of chest physiotherapy to get rid of the very thick secretions which fill and clog the airways. So this child is born with cystic fibrosis, and her mom, in the beginning and later on as an adult individual, they have to do twice daily this form of treatment. And for this 6-year-old, actually, this is the daily dose of medicines they need to take. So there are all sorts of things. One of the things are these 20 pills a day, which are pancreatic enzymes, because these people, although they have no problem in absorbing the food that they eat, they actually cannot digest it. They cannot break down the food with the pancreatic enzymes as we normally do. So before each meal, they need to take a high dose of these pancreatic enzymes. And then there are all sorts of supplements like vitamins, anti-inflammatory drugs, nebulizers, and even, in some cases, enteric food. So what is this disease? So it starts with a gene. I told you it's a monogenic disease, which encodes for a protein which functions as a channel, an ion channel which transports both chloride and bicarbonate. And it works at the apical surface of epithelial cells, and here's the channel transporting bicarbonate and chloride under normal conditions. So in cystic fibrosis, or CF, these are absent or malfunctioning, and the ultimate result is a major impact on the airways of the individuals with cystic fibrosis, because CF, airway disease, is the major cause of morbidity and mortality, and it involves defects in ion transport, of course, because it's an ion channel. Of course, also water transport is defective, so there is a huge dehydration of epithelia and this mucus thickness, which I talked about. And the airway surface liquid, so the thin layer that covers our airways, has decreased volume and pH, so the homeostasis is perturbed. The question is, what is between this devastating airway disease and one single gene of our genome, which is actually mutated? So this leads to what we call the CF pathogenesis cascade, which starts with 2 defective genes, because you need to inherit 1 mutant gene from the father and 1 mutant gene from the mother for actually the disease to show up. So this, of course, encodes for a deficient protein, which is CFTR, is the name of this protein, an ion channel. Of course, ion transport is abnormal, because this is a channel that transports both chloride and bicarbonate, but also because it is a master regulator of other ion channels. Sodium is also dysregulated in CF. So if you notice, chlorides and sodium, that is sodium chloride. So the salt is altered in this disease, the salt transport. And sorry again, and because I don't know how to go back, do I? I do. Okay. And because the water usually follows the salt in our epithelia, there is a decreased water content, so this dehydration of the secretions and the thickening, which I mentioned, and this in turn leads to what we call the cycle of destruction. So this is extensive mucus obstruction, firstly of the small airways, then the larger airways, and bronchiectasis, which correspond to areas which are not where the air does not reach due to this obstruction, scarring of the tissue, chronic inflammation, and extensive bacterial infections. So this leads to the end-stage lung disease, which can only be solved by lung transplant. So most classical therapies, the ones I've shown you for the little girl in the photograph, actually act at this part of the cascade, so anti-inflammatory drugs, antibiotics, mucolytics, and so on and so forth. However, if we want to stop this cascade, we need to act further upstream at the molecular and cellular level. So a little bit of molecular biology of this gene. I told you that is a gene which encodes an ion channel. It is actually one of the largest genes in our genome, so it encompasses 190 kb, which is divided into 27 exons. These are the small pieces that actually code for the protein. And after transcription into RNA and splicing is the cutting and pasting of these small regions, it originates a messenger RNA, which is, of course, much smaller, 6.5 kb. It encodes this protein, CFTR protein, that is the channel of chloride and bicarbonate, which is actually a member of the ABC transporters. This is one of the largest families of proteins in the human genome, but this is the only one which is an ion channel. So after complex folding of this protein and traffic to the cell surface, this protein functions, as I told you, as a chloride and bicarbonate channel. So what is the challenge? In cystic fibrosis, in individuals across the world, more than 2,100 mutations have actually been reported in this gene. So it's very difficult to tackle each and every one of these mutations in this precision or personalized medicine. It's virtually impossible to develop drugs for each of these mutations. So the approach is actually to classify the mutations into their molecular and cellular defect, which I'm not going into detail, but this classification is actually evolving into theratypes. So these theratypes are groups of mutations which can be tackled, if not by the same drug, at least by the same therapeutic approach. And these are some of the molecules. These are how they are called, suppressors, correctors, potentiators, and so on, that tackle each class, rescue mutations in each of these classes or each of these serotypes. So, what is the status at present for cystic fibrosis? So, the majority, although there is this diversity of mutations, the majority of individuals with CF actually have one single mutation that is called F508del, and it is present at least in one of their two genes in 80% of individuals. So for these individuals who have either two of these mutations or just one, there is recently a triple combination drug, so it's one drug with 3 different compounds that actually works for them, at least quite well. For individuals who have one of these mutations, it's called a gating, so it's a defect in the opening of the channel to allow the ions to go through. If the channel does not open, one single drug, actually called potentiator, actually forces the channel to remain open, and it works for them. What about the other sort of almost 20% worldwide? So for these individuals, there is no corrective drug, as we call it, because they're not down at the cascade, they are in the upper part, they have no drug. It should also be said that among these individuals who are also eligible for the other existing drugs, it's estimated recently, in a recent study, that only 14% actually have access to the drugs due to the very high cost. So there is an unmet need for these, at least those 20% of people who have no therapeutic option. And the possibility is to find the right drug through personalized therapies, also called theranostics, meaning diagnosing for the right therapy. So this consists in bringing the right drug to the right person, and the big question is how? So let me give you a few examples of individuals. These are actually real cases which we have studied here in our lab, although, of course, their names are just fake. So this is Paul, male, 39 years, and he has these 2 mutations. We say he is homozygous for this rare mutation. Marie, female, 17 years old, she's also homozygous for another very rare mutation. Anne, female, 24 years. This is actually an American individual who came to Lisbon for us to do specifically this assay. And she has a combination of 2 quite rare mutations. Finally, we have Joe, male, age 26, also with this mutation and another very rare mutation. So what are the challenges here? The challenges are how to find drugs for people with these very rare mutations. The second is we cannot perform the traditional classical clinical trials because there are so few patients worldwide. Actually, for some of these mutations, there are less than 5 individuals worldwide with sharing the same mutation. So it's virtually impossible to carry out clinical trial with such a low number of individuals. And the statisticians in the room will bear with me, I hope. So the solution are what we call the avatars. So what are these CF avatars? These are actually intestinal organoids. So we call them we call the organoids because they're actually living tissues, they're living small organs derived from cells of the individuals. So we start with small, very small, like 1 millimeter colon biopsies. Actually, if you look into a biopsy into electron microscope, you observe these crypts, so these structures which are drawn here, and at the base of these crypts there are LCR5 positive cells. In other words, these are stem cells. And if you know a little bit about stem cells, they have the infinity capacity of dividing, so they don't die, and they can also differentiate into various cell types. So this is ideal material for us for the organoids. So we isolate the crypts from the biopsies. We actually put them in convenient, inappropriate culture medium and in a solid support, and we allow them to grow as epithelial organoids. So the organoids have many applications, and I'm not going into that here. I'm just going to focus on their application for cystic fibrosis. So if you have here organoids, so wild type stands for a non-CF individual. These are organoids for a non-CF individual, and these are organoids from an individual who is homozygous for the same common mutation, F508del homozygous. And if we stimulate the organoids, which of course express CFTR, the gene in question, if we stimulate with a channel agonist, in this case forskolin, we will see that the organoid from a non-CF individual actually swells. And this is 10 minutes, and it continues to swell until more or less 60 minutes. However, if you observe the organoid from an individual with CF, despite the stimulation with the agonist, that it does not swell. So it all comes down to swelling, which is dependent, directly proportional to the amount of CFTR activity present in these organoids for that particular individual. So here we have organoids only from this individual. Here, even without drug, after 60 minutes, there is no swelling, as you can observe. With a combination of drugs, which actually rescue this mutation, you see already swelling. But if you inhibit CFTR, you observe that there is no swelling. So this actually has proven, this is a Nature Medicine paper by the group of Jeff Beekman in Utrecht in the Netherlands, actually demonstrates that the swelling upon forskolin stimulation is directly dependent on the presence of CFTR. So let's go back to our 4 cases. So for Paul, these are his organoids. Actually, after stimulation, they still do not swell much. But if we test these drugs, you can see the swelling actually occurs. And of course, we quantify this, and we observe that this individual will benefit. We can predict from this swelling upon testing of the drugs, we can predict, because it's above a given threshold, as you can see here, that this individual will actually benefit from all 3 drugs, but of course more from the triple combination. So the case of Marie, again, she has this very rare combination of mutations. This is the control. There is no swelling upon stimulation. And after stimulation, after incubation with the drugs, you can see that with this drug, there is some swelling. And again, we observe it is above the benefit threshold, so we can predict that this individual will benefit, but only from this drug. So this avoids the individuals from taking drugs from which they will not benefit at all. 3rd case, this is the American individual. Here, no swelling. There is a little bit of swelling, but not significant with the double combination of drugs. But later studies, actually done by Carlos Farinha's lab, with different techniques, we have shown that this ultra-rare mutation actually responds to this drug. And this individual, she showed the report to the insurance company in the US and actually started taking the drug. She's doing very well. She had a child recently. So we could predict here that she has benefit from the triple drug. Finally, the 4th case, Joe, and these are just 4 examples of the many, many that we have been testing. These are the good cases where we could predict benefit. Again, in this case, this mutation, we already knew it would expect to be a responder, but only when one of the genes has the mutation, we observe benefit, and this individual will also benefit from the 3 drugs, but mostly from the triple combination. So just briefly in 2 slides, I'd like to mention the HEAT-CF. This is a EU project actually led by the group in Utrecht, who developed this approach, and it aims to bring right drugs to the right patients. So what have we done so far? We have collected biopsies from individuals with ultra-rare mutations in Europe across numerous centers, and we collected 500 biopsies from 500 individuals, so this has been already achieved. Then these biopsies have been grown in the 3 involved labs, so that is Utrecht, Leuven, and us here at the Faculty of Sciences. And we have cultured the intestinal organoids and used them in high-throughput testing of novel drugs. So these are drugs which are not yet approved, but are actually using this project to demonstrate the benefit for individuals for whom there is no therapeutic option so far. And this has been done, so we have completed the screens. We have selected the responders among those that were tested, and the Choices clinical trial will start soon, here also in Portugal at Hospital Santa Maria. So in summary of what I've shown you here today is that personalized or precision medicine, also called in this case theranostics, allows that tests in patient-derived organoids can predict responses to approved or novel drugs, matching the right drug to the right patient. The HEAT-CF project uses organoids in high-throughput screens to test novel drugs. So we identified 150 individuals with ultra-rare mutations who are high responders. So there are more that actually respond among the 500, but these are the high responders. And some of these have been randomly selected for the Choices clinical trial, which will start soon. So as a conclusion, organoids, I hope to have convinced you that organoids are a powerful and robust tool to match the right drug to the right person in a personalized medicine approach. So these are collaborators across the world, but of course, Jeff Beekman in Utrecht has been a key person in this collaboration. Of course, funding we have from US, UK, European Union, also FCT Portugal and the Portuguese Association of Cystic Fibrosis. And this is the research group which actually carries out this work and a lot more. This is just part of what I spoke here. And the key people in this project and this data that I've shown you today, one of them has left, has found a job. Good for her, bad for us. That was Iris Silva. She worked in the HEAT-CF project. We have Violeta Heilian, of course, Carlos Farinha, a major collaborator in this project, and many others. Hugo Botelho, who actually does all the mathematical calculations I not show. I told you I will not show equations, but it involves a lot of math underneath the area calculation of the organoids and so on. And Claudia Rodrigues, who more recently joined the group, started her PhD, and she's got a poster outside on this, so I invite you to see it. And thank you very much for your attention.
Então, eu acho que a ciência é uma área que é dividida em várias coisas que é para investigar o que é o mundo atual e o que é que aconteceu há alguns anos atrás. É basicamente investigar o mundo em si.
So time to coffee break. We meet here again in 50 minutes. Thank you.
É a habilidade das pessoas se juntarem e, utilizando um método específico, serem capazes de chegar a uma descoberta nunca antes obtida.
So welcome again. Now it's time to dedicate our time to the second session. Communicating, I would like to invite Marta Santos from the Communication and Image Unit. more specifically from our Science Communication Office.
Thank you so much, Raquel. So communicating science is a fundamental part of doing science. And more and more scientific institutions and researchers as well are aware of this and invest in science communication. And we are proud to say that Ciências ULisboa is no exception. So in this session, we will learn about the experience of researchers, PhD students, and master students in sharing their science. How does it feel for them? As well as how Ciências ULisboa brought them an added value to their professional career. And we will start with a quest that started more or less last August, or at least a few years ago as well, which is an excavation campaign that took place in Pombal, at Pombal, central Portugal, that led to the discovery of what might be the largest dinosaur to be found in Europe. Probably you saw it in the news. The news were everywhere, and not only nationally, they were also everywhere internationally, from USA to Australia. And the campaign involved Portuguese and Spanish experts, and in particular, Elisabete Malafaia and Pedro Mocho, researchers from Instituto Dom Luís, whom I now call to the stage. And we will learn with them more, not only about this discovery as well, but also about the communication process it involved. Thank you.
Good morning. So I'm Elisabete Malafaia. This will be a shared communication with Pedro Mocho. And we're going to talk a little bit about the recent discovery of giant dinosaurs in some localities from the Upper Jurassic of Pombal. This work is part of a research project that we have been developing at IDL that aims to understand the diversity of dinosaurs and other Mesozoic vertebrates from the Iberian Peninsula. One of the main objectives of this project is to analyze the paleobiogeography and paleoecology of the peri-North Atlantic region and to ascertain the main constraints for the evolutionary history of the Iberian vertebrate fauna during the Mesozoic. Another important effort of this project is related with the enhancement of the paleontological heritage. We seek to promote policies for the protection and conservation, as well as valorization of this heritage as an educative, cultural, and socio-economical resource. So the Portuguese fossil record of Mesozoic vertebrates, particularly of late Jurassic dinosaurs, is very rich, particularly in the centro-occidental, centro-occidental region, where several localities are known with fossil remains of vertebrates, but some important localities are also known in the more interior region, such as the region of Pombal that we are going to talk today. One of the first localities known in this region is the Andrés fossil site. In this locality in 1988, it was discovered a partial skeleton of a carnivorous dinosaur assigned to Allosaurus fragilis, which is a species first described in the North American Morrison Formation, and this specimen from Andrés was the first record of allosaurs outside North America and the first dinosaur species described in 2 continents. So it has a huge impact for the knowledge of the evolutionary history of this fauna, and particularly related with the opening of the North Atlantic Ocean. Later, other fieldwork campaigns carried out in Andrés allowed the discovery of abundant new material assigned to allosaurs, but also to several other vertebrate groups. So the presence of such a high diversity and abundance of fossil vertebrates in the same locality is unusual for the Portuguese record and makes Andrés a reference for the study of continental ecosystems in the late Jurassic of the Iberian Peninsula. This material is also part of several thematic exhibitions. Some of them are currently in display in the Museu Nacional de História Natural e da Ciência, and also in several local institutions in the region of Pombal. And more recently, other localities have been discovered with an important fossil record of giant sauropod dinosaurs that Pedro will talk later. In most of these localities, the work still still in course, but several specimens were collected. This is a vertebra of a sauropod collected in one of these localities that is currently part of an exhibition in the Casa da Cultura de Santiago Litém in Pombal. And another locality is the Monteagudo, where recently we found part of a rib cage of an enormous sauropod dinosaur. And this finding was noticed in several media, national and international media. In part because of the exceptional preservation of the fossil remains that were found in anatomical position, that is the position that they had in the animal in life. And another interesting feature of this specimen is the size. It corresponds to one of the largest sauropods currently known in the European fossil record. But together, these localities add important information to understand the sauropod faunas of the Upper Jurassic of the Iberian Peninsula, and Pedro will talk about it now.
Hi everyone, thank you. So let's talk a little about sauropods. So here is Pombal. We have three main fossil quarries that we have been working in the last years: Monteagudo, Moriscas, and Junqueira. In these fossil sites, we found remains of three individuals of a sauropod, of three sauropod dinosaurs that probably belongs to the same species. And they are characterized by their large size. So this is very interesting how we, in these three fossil sites, we have these giant animals. So first of all, what is a sauropod? So a sauropod is a herbivore dinosaur characterized by these long necks and tails with these columnar limb bones, relatively small heads, and it's a herbivore group of dinosaurs. And some of the lineages of this group of dinosaurs are between the largest animals that lived on land. So if you look for this phylogenetic tree, we can see that this group that appears in the end of the Triassic and get extinct in the end of the Cretaceous is the sister clade of theropods that include nowadays birds. So if you look for the sauropod fossil record, this group is probably the best represented dinosaur group in the Upper Jurassic of the Lusitanian Basin, with several and numerous fossil sites already discovered in Pombal region and also in the west region of the country. Sauropods of the Upper Jurassic of Portugal are, for the moment, we already identified 6 taxa. And these 6 taxa are very closely related with the taxa that are present in the late Jurassic of the more recent formation, probably related with the close relationship that these two paleogeographic areas have. So let's look for Monteagudo fossil quarry. That is the one that became famous this August. If we look for this video, let's see if I can do it. So if you look here, this is a 3D model of our fossil quarry, and we can see a set of dorsal vertebrae. This is the anterior dorsal vertebrae, very fragmentary, that are in position with a sequence of 10 dorsal ribs that belongs to the left side of the rib cage. So if you look here in the quarry, we have in the right now, this part of the quarry is already eroded, so we probably lost the neck. That is very informative. And the next years will be, our focus will be working on the left side that probably have the posterior part of the animal. So if you look for this picture and we relocate it, we can see how these dorsal ribs fits in a sauropod body. Another site that is very important for us is Junqueira fossil site. Junqueira fossil site is already finished, but we collected some dorsal vertebrae, and some of these dorsal vertebrae are 1 meter tall. So this is also a very gigantic form, and these dorsal vertebrae are very diagnostic, so we are working now in the study of this material. And the other fossil site that is very promising, it's Moriscos fossil site. In Moriscos fossil site, it's an accumulation of appendicular and axial bones that we still need to recollect this from the field. And if we see from the photos, we see, for example, this giant humerus that have 2 meters, is at least 2 meters long, so we probably are in the presence of another giant form. And if you look for this humerus, we have a very gracile profile that is characteristic from a group of sauropods that we call brachiosaurids. So brachiosaurids, it's this kind of sauropods that have this giraffe-like posture, due to the fact that they have enlarged forelimbs and these specialized skulls with enlarged external nerves. So brachiosaurids in the late Jurassic, in the upper Jurassic of Europe, they are poorly known because they are basically, our knowledge about them are basically based on fragmentary material. So Moriscos, Monteagudo, and Junqueira fossil sites is a fantastic opportunity to study the evolutionary history of these dinosaurs. Another fact that is very interesting is the size. In this case, we believe that the size matters. So when we start to uncover these ribs, we start to compare with other giant forms from the late Jurassic of Africa and North America, like Giraffatitan and Brachiosaurus, and we discover and we noted that these ribs are probably the longest ribs found in the late Jurassic that suggest we are in the presence of the biggest dinosaur ever found in Europe and in the world. But for the news, we decided to be more conservative. Gigantism is a very interesting line of research in sauropods because several researchers are trying to understand how a land animal was able to reach these gigantic forms, and several lines of research are trying to understand how these animals grow, how is the posture and the biomechanics of these animals, and also the pneumaticity. That is a very interesting characteristic of dinosaurs, of sauropod dinosaurs. So, to finish this, what is our next step? So we will need to continue the fieldwork. So we still have a lot of work to do in Monteagudo and Moriscos quarry. Collect all these specimens. We need to prepare them. And after that, we need to start the study that we are starting step by step and describe this material, provide cladistic analysis, paleontological analysis, and morphofunctional analysis in order to understand the evolutionary history of these animals and their paleobiology. All these together, these giant dinosaurs and all the fossil record that was found in Pombal area, we believe that this is very important paleontological heritage for Pombal, and we believe that this could be an important resource for the socio-economical development of these regions. So our next step will be to work together with the localities and institutions in order to musealize all this material and show to the society. Thank you for the attention, and thank you, Beth.
And now we will welcome Ana Cristina Reis. Let me see, do we have Ana Cristina Reis in the room? We do. I was looking on the wrong side. So, Ana Cristina Reis has completed her Master in Molecular Biology and Genetics here at the faculty, followed by a PhD in Biology, specializing in microbiology, and she was one of the awardees of the Best PhD thesis in 2021 for Life Sciences, and she's currently affiliated with C3C. Thank you, Ana. Do you want this one or here?
Okay, so good morning, everyone. So as Marta said, I started my path here at school with my master's degree in 2013. And so 10 years later, I'm still here, so I like really much and I felt really welcome of being, studying and working in this house. So at this moment, I'm associated with C3C, specifically in the group of landscape epidemiology and wildlife diseases. So where we work with infectious agents in One Health framework. So my path started, as I said, with the master's degree. Then I pursued the PhD also working with infectious diseases. So where I studied a specific disease, animal TB, in a domestic wildlife interface. And then I'm here in a position where I'm an auxiliary research. So I continue and pursue it in a research path. And so obviously what I gain here at FCUL, besides the fact that I gained throughout these years technical and scientific competences to develop the work that I'm performing today, which is I keep on working with in research. What I like to evidence is the personal growth that we have during our path in here, and that I think there are competences that are really important if we want to pursue in research, or if we want to move to industry or to other companies. So I would like to say that in here we are forced and we are encouraged to pursue our creativity, to pursue multitasking, to have to learning how to resist the frustration and to always pursue different paths. And I think that is really important when we work in research. So we're always focused in following different types of, in following different paths, in pursuing different goals. And so we are always thinking in the next steps, and also the importance of communicating our work and what we do in here to the community, and what that is important to the society. So in here I felt that since we are in the communication session, that we felt encouraged to communicate our results, not only for a specific audience, but also to the public, so they can understand how science impacts in the daily basis. So that's my testimony here today, and thank you very much for the invitation.
Thank you. Thank you, Anna. We had a third invitee to share his experience with you. Unfortunately, it just tested COVID positive yesterday, but I will just briefly mention his experience. So it was Flávio Oliveira. He also completed his entire academic path here at the faculty, bachelor in biology, master in conservation biology and ecology, and also his PhD in biology and ecology of global changes, and is now working on an ING. So unfortunately, he's not able to be here, but maybe another opportunity will come for us to hear his experience. And now we will switch to the long-awaited time to meet the finalists of the Pitch Your Science, Boosting Sustainable Development Goals Initiative. So I know that some of you have been waiting for this moment. The challenge that we stated a few weeks ago was easily stated, but not an easy feat. We invited the current master and PhD students of the faculty to record themselves in a 3-minute pitch, presenting their research and explaining how they are contributing to sustainable development goals. And the selection process of the finalists was demanding for all the right reasons, because we received many high-quality submissions from various scientific areas. Here are some of the faces of the students that submitted their applications. We actually received 28 applications. Here are not the total 28, because we were waiting for authorizations from everyone, and not all authorizations came on time. But congratulations to all that participated. And we were positively surprised by how the initiative was welcomed by students, but not surprised by the quality of their research and communication skills, because we know we have great students. And today we will meet them and we will see their presentations, and the winner will be decided by you. So pay attention to all communications and be ready to vote at the end of all the 5 pitches that we will see. We have 5 finalists. So think carefully about what will be your favorite, because you can only vote once. And now, so that it is easier then for us to switch between communications, I will call all the 5 finalists that we will have today, and I will kindly ask you to line up here so that afterwards we can switch rapidly between communications. So I will call Ângelo Soares, you can clap, João Mendes, Patrícia Monteiro, Liliana Ferreira, and Micaella Miranda. So congratulations to you all. You are already winners. And just a final word for you, enjoy the experience, and there's no need to be nervous. We are all here roaring for you. So I will call the first one, Ângelo Soares. Ângelo is a student, you can start coming here, is student of the PhD program in Sustainable Energy Systems, and Ângelo studies ground-level ozone air pollution, health impacts, and traffic sustainability, supervised by Professor Carlos Silva from IDL. So you have 3 minutes.
Okay. Hello, my name is Ângelo Soares. I'm a PhD student. The focus of my thesis is on ground-level ozone, its correlation with urban mobility trends, and how does that ultimately impact health. So why ground-level ozone? It is a nefarious pollutant, secondary pollutant. It has health impacts mainly on respiratory diseases. It exacerbates respiratory disease and reduces the quality of life towards later years and the life expectancy. So I want you to imagine the following. How is it formed? You have combustion engines which emit harmful pollutants such as nitrogen dioxide, which through sunlight-initiated reactions produces ground-level ozone. Okay, so now you want to tackle climate change. You want to improve health and well-being. You want to have sustainable cities. Okay, so to fulfill these sustainable development goals, we'll try to curb pollution. So let's decrease pollution. We'll decrease combustion engines. We'll decrease nitrogen dioxide. We'll decrease ground-level ozone, right? Well, that's wrong. That's not what happens. We have created this catch-22 situation for ourselves, where we have decades-old data of this, since the emission standard 01, 2, 3, 4, and 5, 6. We've seen in Europe the decrease of nitrogen dioxide, but ozone, ground-level ozone has been creeping up. We also saw this during COVID, where we abruptly decreased nitrogen dioxide, but ground-level ozone went up. Okay, so we have this negative correlation. And now here's the kicker. Personally, obviously, we have to transition, and I believe that when I go to a city, I don't want to be inhaling exhaust fumes, but we have to be careful how we do it, because if we tomorrow exchange all the combustion fleet by, let's say, electric vehicles, my thesis wants to characterize and understand this. How high will ground ozone level go? Will it plateau? Will it subside? We don't know. And this is the type of question that I'm trying to answer with my thesis, so that we can characterize the past, the present, and forecast the future, so that with good data, we make good policy and we can make a careful and well-done transition. So that's the purpose of my thesis. Thank you very much.
Okay. Thank you, Ângelo. And now it is time to welcome João Mendes, who is pursuing a PhD in biomedical engineering and biophysics. And how can we improve breast cancer risk prediction? Well, João is working on this research question by combining multiple imaging modalities. And he is supervised by Professor Nuno Matella from IBEP and Professor Nuno Garcia from LASIS.
Hi, everyone. So imagine that it was possible to predict when you will get seriously ill. How serious? Well, the most commonly diagnosed type of cancer in 2021, breast cancer. The goal of my PhD project is to predict, based on medical images, the risk of women to develop breast cancer. And when I'm talking about predicting, well, I'm not actually talking about like astrology, but real science. In fact, I'm going to use artificial intelligence. And if you don't know what that is, well, it's just a lot of math equations put together to create a model that learns stuff. But what will it learn? Well, this model will look into a lot, and when I say a lot, I mean like 100,000 medical images, like MRI, ultrasounds, mammograms from different patients and across several disease stages, like from an healthy stage until a cancer stage, in order to learn breast patterns and specific features that characterize those stages. And a solution like this one would allow us to gain something that is of extreme importance when we are dealing with cancer: time. Well, most screening programs aim to do that, but they are very standard and might not serve all women. So a solution like this one, based on risk, would allow us to adapt screening programs both in periodicity and in image technique methodology used. So the outcomes? Well, an early diagnosis, a better prognosis, and a global diminishing both in stress levels and financial burden that comes with this disease. But the use of a diverse range of medical imaging modalities is not the only diversity factor present in this study. Incidence rates in breast cancer continue to grow each year. And although the incidence is higher for white women than for any other ethnicity, when it comes to death rates, black women are the most affected group. And while one might argue that that is only due to genetics, it would be wrong, to say the least, to overlook the social disadvantages that these women face. They have access to lower quality health facilities that are short-staffed, that have less trained doctors and outdated machinery. All these factors combined lead to a longer waiting period until a final diagnosis is met. Once again, this is where my PhD project can make a difference. A medical solution like the one I proposed would allow us to gain time for every woman and to improve diagnostic accuracy by adapting screening. Once again, this is a computerized solution, so it can be used in any medical facility, and it will help to even the balance in what comes to diagnostic accuracy. So there you have it. My PhD thesis not only aims to diminish inequalities, but also tries to democratize the access to what is a fundamental global human right, quality of health. Thank you very much.
Thank you, João. And now we switch to Patrícia Monteiro, who is working in the field of history and philosophy of sciences. Olive cultivation and olive oil production are key in Portugal's culture and economy, and Patrícia is uncovering its history with the supervision of Professor Ana Duarte Rodrigues from CIUCT. So we welcome Patrícia.
Good morning. It's an immense pleasure to be here. Thank you. So, the olive cultivation phenomenon has been used to define the Mediterranean frontier in the imaginary of populations. Focusing on olive cultivation in Portugal, my research tackles the change of traditional practice into olive-intensive growth and how this has impacted on environment and on the interface between man and landscape. My PhD research project aims to understand of the scientific and historical technique of olive cultivation in Portugal from the perspective of the history of science and technology, along with this interface with environment and landscape studies in the early modern period. Therefore, I went back to a Latin agronomist who wrote about it in antiquity, but whose texts were further disseminated in 15th and 16th century. So, Columella wrote about a rudimentary method of producing olive oil called canalis et solea, which consisted of stepping on the olives with shoes on a piece of wood where the liquid drained out. The same technique is described in a Portuguese 16th century book entitled Corografia do Reino do Algarve, written by Frei de São José. Until today, the same technique is used in small communities in Portugal. However, these traditional methods are almost disappearing due to the rise of intensive olive cultivation. The internationalization of the olive oil industry and the search for cheaper productions have led to a process of technological advance replacing the traditional methods of olive growing up in the oil production. Nevertheless, this changed dramatically the relationship between man and environment, as well as the way of life of rural populations. On the other hand, the traditional olive oil production cooperatives are valued and are in the strategic debate on the production of extra virgin olive oil, an overrated item worldwide. Briefly, the Spanish olive landscape will become a UNESCO World Heritage. Portugal could follow the same path and value its landscape as people and environment. The research aims to provide a database necessary for the debate on the preservation of the identity of the territory and its sustainable productive character. Therefore, it's included in the Sustainable Development Goals with emphasis on responsible consumption and production, and sustainable cities and communities, especially the target strengthened effort to protect and safeguard the world's cultural and natural heritage. Thanks again for the opportunity.
Thank you, Patricia. And now we call to the stage Liliana Ferreira. Liliana is a PhD student in biology, and she is developing tools for conservation planning by studying bats, landscape configuration, and climate change. In this project, she is supervised by Professor Jorge Palmeirim from CFTC and Professor Sarah Cousins from Stockholm University.
Hello, everyone. My name is Liliana, and I'm a PhD student. I'm enrolled in the PhD biology with specialization in conservation biology, and I am studying bats. My thesis is focused on the effects of landscape configuration and climate change on bat species presence and their distribution in Scandinavia, so along the northern distribution limit of these mammals. With just this brief introduction, I think you can already see which United Nations Sustainable Development Goals our work will contribute to. So Goal 13, climate change, and Goal 15, life on land. Goal 13 states that we need to take urgent action to combat climate change and its impacts. One of the objectives of our project is predicting the impacts of climate change on bats along the northern edge of distribution. And with this objective, we want to understand which climatic variables are more likely to impact bats during the ongoing climate change process, map future bat species distributions and changes in species richness, quantify total potential range area for each species, determine which percentage of the current range will remain with suitable conditions for the bats, and also rank Scandinavian bats according to their sensitivity to climate change. With this research, we'll be able to have a clear understanding of how the different bats will be affected by climate change and how they might respond to the changes. We know that the climate change models predict that the species that are adapted to the northern conditions will decline in the southern part of their range, and the center of their distributions will retreat northwards as the temperature increases. Bats are expected to respond to global warming in accordance with these predictions, but this response will vary across species and habitats, and that is also where this research is so important. Moving on to the other Sustainable Development Goal that our work will contribute to, so Goal 15, life on land. This goal states that we need to protect, restore, and promote sustainable use of terrestrial ecosystems, to sustainably manage forests, combat desertification, and also halt and reverse land degradation and halt biodiversity loss. This is a very complete goal for life on land. For this goal, my thesis objective that I just told you about will also have an important contribution, as knowledge on how the different bat species will respond to climate change, where they are and where they will be, and how sensitive to climate changes they are, allows to develop species conservation planning. And with species conservation planning, we concretely know what to do to protect the different bat species, these cute and very important mammals that not only have intrinsic value on their own as living beings in this beautiful world, but also perform very important ecosystem services. Thank you.
Now, thank you, Liliana. And last but not least, we conclude this row of amazing presentations with Micaella Miranda, who is pursuing a master in molecular biology and genetics. And in particular, she is studying the impact of cell matrix adhesion dynamics in NIS residency at the plasma membrane. And she's supervised by Professor Rita Zilhão from C3C and Professor Ana Luisa Silva from the medicine faculty.
So, hi there. As said, I'm Micaella Miranda. I'm a biologist, and I'm currently developing my master's thesis. I am in the Masters of Molecular Biology and Genetics. So my master thesis is aligned with one of the 17 Sustainable Development Goals of the United Nations, which is good health and well-being. The main topic of research of the group I integrate is thyroid cancer, a pathology that unfortunately has considered to be the third most prevalent among Portuguese women, and according to the Cancer Organization in the year 2020, 586,202 people worldwide were diagnosed with this type of cancer. Currently, there are only two main types of therapy for this cancer. The first is a thyroidectomy, where the thyroid is partially or completely removed. And the other alternative is radioactive iodine. And no, the patients don't stay glowing green. So how exactly does the radioactive iodine treatment work? Well, basically, for our thyroid to function, iodine is needed. And therefore, we have a specific protein that is named the sodium iodine symporter that is located on the cell membrane and is responsible for the simultaneous transportation of sodium and iodine from the exterior of the thyroid cells to the interior. It is through this mechanism that the radioactive iodine treatment takes advantage of a natural behavior. And through this, it is capable of entering, attacking, and killing the thyroid cancer cells. However, this protein is not always present on the cell membrane, rendering radioactive iodine treatment to not be as efficient as hoped. So with my master thesis, I intend on studying how extracellular matrices, so basically how different proteins such as laminins and integrins that work as the scaffold of the cell, providing structure and support, are capable of increasing or decreasing the sodium iodine symporter stability and maintenance on the cell surface. To do this, I use cell culture, aligned with Western blotting, which is a technique that allows me to determine the amount of protein present in the cell. And I also will use immunofluorescence, which is another technique that allows me to use fluorescent dyes to visualize the cells and also to visualize the protein and where it is localized. And in this case, the cells do glow green, unlike the patients. So hopefully my results will shed light on how we can improve the treatment with radioactive iodine for patients with thyroid cancer. Thank you so much for your attention.
Thank you all. And now that we have had the opportunity to learn a little bit more about the work that each of you is developing, it is time for you, the audience, to vote on your favorite communication. And just before I explain you how you're going to do that, just to mention that the order by which the presentations took place is no particular order. It was just randomly that we selected this order. So, how will you vote? You'll pick up your phone, please. Now you have green lights to pick up your phone, and you will go to your internet browser and go to the website www.menti.com. And you will put this code that you will have here. I will now have to switch slides, so if you don't see the code yet, don't memorize it. It's no problem, because you will see it in a few seconds. So this is the Mentimeter is the system that we will use to vote. And as you see, there is a window going there. Let's pray that everything goes fine. Ta-ta-ta. There it is, see? And now, you will see the code. You will see the code there. Just in the top of the screen, you have the code, which is 34478173. And we have hidden the results. That's why we already have 15 people voting, but you don't see the results yet. You will see when everyone has voted. And while we wait, just to mention again that it was a difficult process to select these finalists because we received many and very high quality participations. And when I say we, I mean, first of all, the directive board and as well as the communication and image unit. And we were very happy to see how well this initiative was welcomed by you. And without spoilers, you can be certain that this will not be the last time we will have such an initiative. And so, we have 77 votes. I'll just give you a few more seconds, so be quick to decide which of the communications was your favorite. And our 5 finalists are Congratulations to you all, because it was amazing. And we have one doubt there. Let me just run to that question there. The order was Ângelo Soares, João Mendes, Patrícia Monteiro, Liliana Ferreira, and Micaella Miranda, just as it shows in the screen. And so we have above, I will give you 20 seconds to vote. Is that okay? Because we are rushing out of time at the program. So I'm counting the seconds now. And we have 110 votes. No more votes are coming, so now votes are coming, okay. We have some people that were late deciders. And now I will close the voting, and we will see the winner. Let me, it's not, aha! So João Henning Mendes is the winner. And I call to the stage all the 5 finalists, because we have certificates and a small gift bag for all of you, and the surprise prize for João. Thank you. And I also call to the stage Professor Pedro Almeida to give the awards. Thank you. So thank you, and congratulations to all the finalists, and stay tuned for future initiatives. And that's all from my part. Thank you.
So we need to move quickly to the next section because we are delayed. So we are also innovating in a way of presenting things. So we will have now a presentation which is coming from Chile directly. You can make the connection. So as Francisco Lobo told us this morning, Alexandre is already in Chile preparing the instrumentation in the observatory, MOONS, and he's going to speak us a little bit about it just in a minute. Thank you very much. Alexandre is from the Institute of Astrophysics.
So hi, Professor Alexandre.
Hi, good morning. Bom dia.
Morning. So people are listening you, and now they are seeing you directly from Chile. So I'll give the floor to you, and you can share your slides whenever you're ready.
Okay, so I think I started sharing now. So can you see the screen now?
It's okay. Yes.
Okay, let's try to not to delay a bit more. So good morning, everyone. I'm currently in Chile for the starting of the installation of the next multi-object spectrograph for the Isoperenal Observatory, and I will try to show you a little bit of what we are doing here and why we are here. So in fact, I'm talking on behalf of a largest team, and the interesting part is that it's both a team of people that are coming from engineering physics and also our other colleagues that are coming from astrophysics. So in fact, we are dealing with the state of the art, not only on the technology and on the research done around the technology, but also on the astrophysics. And any question on astrophysics, you can ask my colleague José Afonso, that is certainly there, as I will keep mainly on the points related with the engineering physics. So the MOONS is a multi-object spectrograph. So it's a spectrograph that will observe several objects at the same time, and is going to be installed in the European Southern Observatory Very Large Telescope. This is essentially the most advanced optical observatory in the world, and is located in the north of Chile in the Atacama Desert. in a mountain that is at 2,670 meters of altitude. On this image, you can see 4 of the really large telescopes that exist. So the complex, the observatory, has several telescopes. Each one of these largest buildings has one telescope with a mirror that the primary mirror that defines the amount of light that can be gathered. And we're talking about an 8-meter telescope. So we'll talk about the largest size telescopes in the world. Moons is going to be installed on this one here on the left. So it's on the UT1.
Good morning, everyone. So the Science Research Day is tomorrow, but it's really impossible to have any connection here. So this is recorded one day before. So we are here in the middle of the Atacama Desert in Chile. So in the middle of nothing, but to have this incredible infrastructure, the observatory of the ESO Observatory, the very large telescope. And this is what we are going to do. We are going to start the installation of one instrument, Moon. And you see here behind me these 4 telescopes, 4 8-meter telescopes. So inside each one of these telescopes, we're going to see in a few minutes, there is a huge 8-meter mirror. And on this one here, the first one, UT1, is the one that we are starting now to install the first element of moons, the next multi-object spectrograph for the VLT.
Okay, so this is to say, and you probably already understand, I'm on the room, and mainly because it's really hard to have any proper internet connection. This next slide is also to give you an idea of how remote the place is. So the observatory is what you can see pointed on that arrow there. So we are really, really in the middle of nothing. And it's almost like working on Mars, also for the color, with a bit more oxygen. It's something that is interesting, and it's also one of the reasons why we are here, is that the visibility is incredible. On this image, you can see on the top, in the middle, that is a volcano that exists in the border between Chile and Argentina. So it's about 200 kilometers from here. And I can tell you that yesterday on the platform, we could see that there is almost no snow, while on this picture, we saw some snow. So it's really clear. Of course, the sky on the southern hemisphere is also more interesting for my colleagues, astrophysicists. So it's those two main reasons that take us here. Of course, this is not only telescopes. We have telescopes, and as you can see in the bottom picture, there's an infrastructure that has, for example, the integration hall where we were yesterday and going tomorrow, and there is also a residency where I'm currently in one of these rooms here. And probably some of you already saw this residencia on the Quantum of Solace. So it's one of the buildings that explode. Fortunately, it was only on the movie. Everything is okay, but it's something that is really interesting because this is essentially like a city that has to live in an independent form. So who is building moons? Moons is a large consortium led by the UK Astronomy Technology Centre in Edinburgh. And the Faculty of Science and IA is also participating on this construction. And there are several subsystems, and each institute is contributing to different subsystems. In terms of science, as I said, this is not my area of expertise, but essentially we're trying to answer 2 questions. How do stars and galaxies form and evolve? And do we understand the extremes of the universe? This is just a simple example of a graph that just shows what is happening with other instruments and what moons will be able to provide. So moons, these red points here, will be able to provide information and will allow us to do science where currently there is no instrument with the capability to do it. In fact, this region in the redshift is even called the redshift desert, and moons was designed for that, and is all these challenges that define what has to be this instrument. And just to mention a few of the main requirements, the way to answer those questions led us to design a 2 triple-arm spectrograph with a spectral range that goes from the visible to the infrared. It's really a very complex and very large spectrograph, the largest that will ever be installed here in Paranal. A really large field of view, 25 arc-minute diameter field of view. This corresponds to the size of the moon, and that's the origin of the name for the instrument. In a 25 arc-minute in an 8-meter telescope, because we will need a lot of photons, and also as we want to observe a lot of objects, the idea is that we can observe up to 1,000 objects at the same time. So the light that is gathered by this 8-meter telescope has to be inserted in 1,000 fibers that will have a diameter of a human hair. So we're talking about 1/10 of a millimeter. So this is the internal view of the inside view of the telescope. And here you can see a model of what is going to be moons inside one of these telescopes. So here you can see part of the front end, part of the spectrograph. Essentially there are 3 subsystems, 3 critical subsystems here. One of them is a field corrector that we cannot see here on the right side, but it's essentially a big lens that is doing to the telescope the same as my glasses are doing to me, because the field of view is so large that the telescope cannot give a proper image quality in the limit of the field of view. So we need to correct that with the largest lens that are being built nowadays. And then we have the front end, and the front end is a complex system that manages the light that is coming from the telescope and provides several functions related with metrology, etc. And at the end, the light has to be inserted on fibers that are then routed to the large spectrograph that you see here on the left side. The field corrector that I already mentioned is one of the systems, the subsystem that is under the responsibility of IA and the team from the Faculty of Sciences. And we are currently now installing this part of the instrument. And it looks like a very simple corrector, just 2 simple lenses. But we're talking about a lens with almost 900 millimeters. So it's the complexity, the tolerances, and all that is really critical. So we had to design, we had to tolerance everything, and the manufacturing was done in Italy, in Officina Stellare, and this is one of the videos during the process of manufacturing. It's very critical. The tolerances are very, very small, and essentially we are doing something, and the company was also doing something that was never done before. There are similar correctors, but not with the characteristic that we would need for this one. So we are currently we are always developing things in what is the state of the art. Of course, these big optics will have to be attached to the telescope. This is an example of the structure that we're going to use. Is a structure made in a critical material, and it was not easy to do. It was done in manufactured in Cunhol, a company near Lisbon, that also did all the remaining parts of the structure of the rotating front end. And the rotating front end is the other part that IA and Ciências is responsible for. And essentially is a big structure with mechanisms, some electronics that allows us to provide moons with all these different functions that I already mentioned, like the metrologies, the retraction, etc. And here you see an image of the testing that was done. These were images from the first floor of the C8 building, and an image of when we were after integrating everything. So putting all the Lego bricks on this structure, and the way to try to, after assembling it, put it in the right orientation in the small labs that we have in the faculty. I'm saying small because, as you can imagine, later this is already in really large labs in other instruments. I mentioned that the front end will support several subsystems, and this is one of them, is one of the most important. There's a plate that will weigh 350 kilograms, and that will have 1,000 robots. What you're seeing is 1,000 robots that will support the fibers, and they will provide the ability of the instrument to locate the fibers where the objects will be, where the galaxies will be, for example. So on that tip, there are some marks for the metrology, and there will be a very tiny fiber that will be located where the object will be. Here you see there's only 2/3 of the 4 fiber positioning units installed, and here you see the dance that they have to do when you have to go from one observation to another. So when they finish observing 1,000 objects, they will have to move to another object, and this is one of the critical systems. So think about something that is smaller than that is like 100 micrometers in dimension, and installed in a system that is like 2 meters, 2 tons. So we go from really big things to really small ones. And also the spectrograph that is being manufactured by our colleagues from UK, from France. And here you see the size. This is just the optical setup, is really, really huge. And just to give an idea of the size, I'm not very short, so you see that is really huge, and is something massive. We're talking about close to 4 tons that are going to be installed in the telescope. So you can imagine putting all these and the stability that all these things have to need in this telescope. Trying to go inside the telescope.
So now we are inside the telescope. So in one of those zones, the UT1, and here you can see the telescope. This big structure is the 8-meter telescope, and on the top you can see a smaller mirror, the secondary, which is 1.2 meters. Okay, so now you can see the big telescope, big mirror, M1 mirror here on this position, and then the light is diverted to the secondary, the 1.2 meters. And then from there it goes to that mirror in the center. It's a flat mirror that just allows us to select the light towards one instrument or to the other one. And that is the platform where we're going to install moons. So we're going down now and then going up again to show you in the platform the area where we're going to install the instrument. And here, this is the location where we are going to put this new instrument that I already showed you the model. So on the model you can see that the big structure, the spectrograph, is going to stay on this side, very, very tall. So it's like it will reach that level. And this is where the rotating front end is going to stay. And the field corrector, the lens that we are installing on this mission, is going to stay here on this part, and it's going to be a lens 1 meter on this position.
Okay, so that was yesterday, and this was in July. So I'm just trying to cover now at the end the current status. So this was July in Ciencias, big packages being sent to, this one is being sent to Edinburgh. Other packages were being sent here to Paraná, and this was September in Edinburgh. Here we have, as I said, is a much bigger lab where we can install the rotating front end in a telescope simulator. And here we do a lot of tests, really a huge amount of tests. Everything has to be tested before it's shipped to Chile. On the right side, you can see that the rotating front end and the spectrograph, they are now very close together, still continuing to do independent tests. And this is what is required to make sure that when things arrive in Chile, everything is working as expected. There are always surprises. This is one of the interesting tests we had to do on the system that we developed, and it was a new idea to manage the fibers that are rotating in the rotating front end and the way they will reach the spectrograph. The fibers are very, very sensitive, and we need to guarantee that nothing creates any stress on the fibers. And this is one of the funny tests that we had to do. So today, and in fact, these pictures were done yesterday, but this is what we are doing today. So the field corrector was unpacked already. We are in this integration hall here. And on this image, what you can see is Inês. Inês is a PhD student from Ciencias on engineering physics. She did all the degrees in Ciencias, so she's taking now the opportunity to be on these really nice places. She's seated on the box with the structure, and the structure is here.
So this
now.
is the current status of the field corrector for moons. This is the structure, the one that was manufactured in Portugal. This is what is going to be attached to the telescope. And on this side, we have the field corrector. So this is, as you can see, really a large lens. And this lens tomorrow is going to be inserted on this structure. The tolerances are very, very, very small. So we have to be very, very careful. This is an incredible piece of optics. And we have to be very careful. So this is the current status of what we are doing. So at the end of the week, we will have this in the telescope, and we will be doing the tests. And after those tests on the telescope, we'll go for a star, and we'll do the first night tests to commission the structure. Just one thing that I have to say, I'm not here alone. Inês is also here with me. So she's a PhD student at the faculty at Ciencias on engineering physics. So if you want to do nice stuff, you can do a PhD in engineering physics and play with all these incredible toys.
Okay, so, oh, sorry. So I hope I didn't exceed my time, and thank you all for your attention, and I wish us luck because we will need it on the next days.
So thank you. Thank you very much, Alexandre. It's very much better to see the things on the side than just slides. Thank you very much. And have a nice journey over there. So I call the next speaker. Thank you very much, which is Ricardo Mendes. He was a former member of LASIG and is now working on Tech Labs on one of the spin-offs of the faculty, and he's going to speak about a case of success, which is VOLT.
So, today I'm here to talk to you about our journey from researchers to startup founders, okay? We started as researchers here in LASIG, as she mentioned, and we did our research here, and at some point we kind of were challenged to take this idea, create a product, and go to the market. So before anything, what is VOLT? Okay, VOLT is a solution to store data, focusing data protection in multi-cloud and hybrid cloud environments. So simplifying everything from the moment these IT managers have to extend their IT infrastructure all the way down to the storage itself, resilient, secure, and cost optimized and performance optimized, everything built in, okay? So, from the very beginning, we started back in 2011, and we started by creating our first storage system, our first file system that stored data in multiple clouds, okay? That was fault tolerant, that provides a lot of guarantees in terms of consistency, resiliency, fault tolerance, cybersecurity, all of these concepts. Okay, it was targeted to small files, to very critical files, and we published it in a Core A conference. It was pretty cool to have this experience. But after this, what we saw was the need to extend this system and simplify its management and deployment to big data, to large amounts of data. Then we created Karen, okay? So our second, if you want, the second step of our journey to create VOLT. This system for sharing big data, this was developed in the context of an European project called Biobank Cloud. So the problem it solved at the time was how to store genomic data, large amounts of data, very critical data in a multi-cloud fashion, ensuring that all data is always secure and not even a byte is ever corrupted or lost. Okay, with this system, and it was at this stage that we were kind of, our partners started to challenge us so why don't you try this in the market? Why don't you try to pitch this to investors and see what the market has to say? So there's already in place, and still it exists, right, Rita? So the Science into Business contest, in which they receive some ideas, some business ideas, and the idea is to select the best each year. And then with this, with this system, we were there and we got our second place. So as you can see, younger and with some less kilograms, as you can see, still tall, okay? So we learned a lot. In the first edition, we got the second place. We learned a lot of the needs, or the key pains the market had in that space, but we learned also regarding the problems our product would have when launching it to the market. And then we go to the lab, and then we, in the context of another European project called SuperCloud, we created Janus storage. And this system was, we bring to this system the concept of optimizing costs, reduce costs, keep costs low. Everyone wants to have secure and resilient systems, but the cost is an important part. Okay? And then we created this system in which the customer had, or the user have the opportunity to specify their needs, their requirements, namely to the geolocation, namely to the data stage of the life cycle, and the price and the costs are then adapted to the customer needs. Okay? With this, we went again to the Science into Business, and guess what? Second place, okay? So the key takeaway here, and at this stage we were already started searching or trying to get investment, and we were involved in, by the way, we were there, myself, Tiago, and Alison, which is a full professor in informatics department here, and actually I think it's now the president of LASIS, and still a founder and still involved in the company as of today. But what I was saying is that at the time we went to a lot of context, a lot of programs to get validation, to get feedback, to learn, and yeah, we got some interesting places and achievements and so on, but we didn't won once, okay? We do not get any first place. So the first takeaway here is do not give up when you don't win, okay? Sometimes you don't. In our case, we never didn't, okay? So, but guess what? We managed to have our first investment in May 2019, and we started our journey as a company, creating our product from our prototype developed here in this house, and getting our first customers. Now we are starting to grow. So now, of course, with a lot of challenges, a lot of things to do every day, but again, we managed to start this and start this journey. Well, it will end somewhere, hopefully successfully, okay? So, from research, prototype to a product. That was the first step and the first challenges we had to handle at the time. So, and I'm totally leaving out all the business part. I'm only talking about the product, okay? We have a prototype that is kind of working, but we need to create a product to put in the market. So, first of all, branding. We need to communicate. We need to tell people who we are, and what are the problems we solve. Very briefly, very clear. That's the first goal. Second goal, and it's pretty operational, if you want. So, nothing comes from nowhere, okay? We as researchers, and myself as a former researcher, we take a lot of assumptions. So we assume that this will happen in this scenario, with this workload, with this type of data, with this, in our case, of course. But with a product, you can't have this, okay? There's heterogeneity, there's a lot of systems, there's a lot of things happening in the market, and you can't assume anything. So you have to have everything implemented. After this, design, UX, all of this is important, and is linked, of course, with the branding, but looking good, looking very simple, because it's very important for the users to, or the customers to understand what you are doing in a couple of minutes, okay? And billing, which is very important, because at the end of the day, companies want to make money. And trust me, make it easy for customers to give you some, okay? if it's hard, they will not do it, okay? So, 3 key lessons from our personal experience. First of all, look, we just heard 5 very impressive projects here. I'm not saying that all of them can have a place in the market, but some of them certainly do, I imagine, okay? So do not take your projects, do not let your projects in the closet. So go outside, talk a bit about this, and if you have this interest, go ahead and try. It is fun, okay? But hard, okay? It's hard. All days have challenges, from investment, from marketing, from sales, from all of this stuff. We don't learn this kind of stuff in the faculty. We don't know how to do most of the things we do, okay? But at the end of the day, we still manage to do it. It's hard, but it's worth it, okay? Because at the end of the day, you are here to learn, we learn, and we are capable to achieve what we don't think we were able to achieve. Okay, that's it.
So thank you for all presentations. Now let's go for lunch. I tell you that at the C3 Atrium you will find posters about science developed here at Ciências ULisboa, and also we invite you to participate in the side events related to research in Ciências ULisboa. In the afternoon we will be continuing, so we invite you to meet here again at 3 o'clock. See you in a while.
Construir coisas. Para mim, a ciência é quando juntas 2 produtos químicos e faz aquilo uma explosão.
So we are back. Thank you. Welcome again. We will continue the day with Professor Margarida Santos Reis, our Vice-Dean, and the session 4, Co-Etting Basic and Applied Science.
Thank you very much, Raquel, and thank you all that are here already. So we will start this afternoon session, which the idea is to give the word to all the scientific areas that we have here in the faculty, as I said, from the fundamental to the applied science. And we will start with mathematical sciences. And I invite Professor Carlos Florentino from CMAFCU to give his talk about geometry, algebra, and please come. Thank you very much.
Okay, so hello, good afternoon. I would like to thank the organization of this event for the invitation. For me, it's a pleasure to talk to this diverse audience and scientific audience, nevertheless. And but it's also a challenge, right? It's a challenge because I want to present some mathematical ideas, but I need to keep all the technical details to a bare minimum. And but still I want to convey some interesting concepts of mathematics and ideas, and give a glimpse of what would be, an idea of what can be mathematics, or some themes in mathematics that, some topics in mathematics that are in the intersection of geometry, topology, and algebra. And so there would be many possible choices for this general talk. And I decided to talk about mainly two concepts, curvature and the other characteristic, which I think they are good candidates to give you some intuition and explain things without detail. Then I'll talk a little bit about commuting matrices and present some, in the end, some outlook and some conclusions, maybe some open problems. Okay, so what is curvature? So start with a plane curve, a curve in the plane, take a point. At every point of the curve, there will be a circle, a unique circle, which best approximates the curve in that point. That's the oscillating circle. What is a curvature? The curvature is just the inverse of the radius of the oscillating circle. And this coincides with our intuition that if the oscillating circle is very small, then the curvature is very big, and vice versa. And at a portion of a straight line, let's say the curvature is 0. Okay, what about surfaces? Okay, so this was the idea of Gauss. Gauss thought of the curvature in a surface, and his idea was take a surface in 3 space, look at all possible slices of that surface that are perpendicular to the surface at a point, and look at the biggest circle of that curve, and look at the smallest circle of the curve, take their curvatures, multiply. And that's the scalar curvature, also called the Gaussian curvature. And I put there a plus and minus sign, because if the circles, one is one direction, and the other circle is on the other direction, then the curve will be negative. Okay? So what was his theorem with his definition? Was the following. The scalar or Gaussian curvature only depends on the metric. This means it only depends on the distances measured within the surface. So basically, it does not depend at all in the way that the surface is embedded in space. For example, I forgot one very simple example. This piece of paper has 0 curvature because, of course, if I put it flat like this, then, we have a 0 curvature. But if I bend it, it still has 0 curvature because one direction at least is 0, and 0 times everything is 0. So I can bend slightly a surface, and the scalar curvature is invariant. He thought that this theorem was so nice that he called it Theorema Egregium, like the nicest theorem he could show about surfaces. Okay, however, the curvature is not invariant and the stretching. Why? Because if I have a balloon, or let's say a sphere, and it has a radius, I increase the radius, then I decrease the curvature, so the curvature is not invariant. However, there's a very interesting notion that's going to be invariant. It's a total curvature of, let's say, a closed surface. It's just the integral of the curvature along the whole surface. And that's going to be invariant. This is something that I think Gauss didn't really think too much about it, but neither Bonnet, apparently, but it's now a very famous theorem called Gauss-Bonnet, and it says that the total curvature is invariant under all deformations except cutting or gluing. So this is an example of, deformations, and the total curvature of those surfaces is the same, regardless of the area. Okay, so one then computes, of course, this computation is not trivial, that anything that's deformable to a sphere, the total curvature will be 4 pi, because if I take a sphere of radius 1, then 4 pi r squared is the area of the surface, so the curvature is 1, so there's the 4 pi. Then if I take a torus, the curvature is going to be 0, because inside the torus there will be negative curvature that compensates the positive curvature outside. If I take a 2-hole torus, etc., the curvature starts being negative, and if I take a torus with g-holes, the curvature would be this formula, where chi-s appears. What is chi-s? The Euler characteristic of a surface. And why do I write it like this? It's because there's another interpretation of this Euler characteristic, by Euler, of course, that comes from studying convex polyhedra. if I study, of course, any convex polyhedra, then I take the number of vertices, the number of edges, the number of faces. This alternating sum always equals to 2. But putting together the two kind of observations, we get that we can do anything for any surface, not necessarily convex. So if I take this surface, well, it's like a weird surface, but it's like not really triangulated. Let's call it quadrangulated, but that's fine. I mean, we can just compute the number of vertices, edges, and faces, and it will give 0. Why? Because it's a deformation of the torus. And so we get this another form of the Gauss-Bonnet theorem. Okay, so now, what about polynomials? What do polynomials have to do with this? Well, okay. Let me just say that some polynomials, like this one, x squared plus y squared equals z squared, have many, many solutions. Those are called Pythagorean triples. There are infinitely many such triples. We also have a very famous result saying that this equation, as long as the exponent is bigger than or equal to 3, there are no solutions to this polynomial equation. No solutions in integers. Okay, this is the main point. And this was Forbat-Lass theorem in quotes, and it's of course called now the Wiles-Taylor theorem from '94. More interestingly, at least from my point of view, is the following question: how many integer points are there in that solve a polynomial equation like this one? X squared plus y squared equals n. And famously, Jacobi presented the complete formula for the number of solutions. D1n is the number of divisors of n which are congruent to 1 modulo 4, and D3 are the number of divisors of n congruent to 3 modulo 4. And if you take this circle here, which I wrote as being as having radius 5, then n is 25. The divisors of 25 are 1, 5, and 25. Both are, all three are congruent to 1 modulo 4. So we have 12 points here. This is a very interesting theorem by Jacobi. Another very interesting theorem on this kind of question, much later, Faltings, he won the Fields Medal for this theorem, is that the first glimpse of a strange relation between the Euler characteristic and the number of solutions of polynomial equations. This is something I cannot explain in all detail, but let's take a polynomial with integer coefficients that describes a smooth surface with Euler characteristic negative Euler characteristic, which means that the genus is at least 2. Then it has only a finite number of, let's say, integer solutions. What I'm not explaining is how can you get this polynomial to describe a surface, because I'm not talking if x and y and z are real numbers, complex numbers, or whatever. But anyway, you can see that this equation, initially, you can think of it as a circle, right? So take 3 variables, you can think of it as a surface in some way. And it's just that I want to solve the question for integers. But if I take real numbers or complex numbers, it will describe what is called a manifold. Anyway, but the theorem is still amazing. The fact that the Euler curvature is, the Euler characteristic is negative gives a finite number of integer solutions. So more generally, one can define the Euler characteristic for any space of any dimension. And in particular for this space is called algebraic varieties, which is just, at least for this talk, the set of solutions of a system of polynomial equations in many variables, a finite number of them. Okay. And I want also to give this definition, which is of a Lie group. A Lie group is a very important concept because it quantifies the notion of symmetry. Symmetry in physics and symmetry in in fact, this has been applied also to chemistry and so on. So a Lie group, for me, this is a simplified definition, is a closed subgroup of the group of invertible matrices which have determinant different from 0. 2 examples. One is the space of all invertible matrices, let's say with complex coefficients. The other one is the space of orthogonal transformations in Rn. Thus satisfies A transpose times A is the identity and the determinant is 1. And I like to call this the nicest theorem that doesn't have a name because it's a relation between, it's a computation of an Euler characteristic of a Lie group. When it's compact and has positive dimension, then the Euler characteristic is 0. Well, some interesting result. And of course, I would need to define the Euler characteristic for a higher dimensional space, but it's in the same way. I triangulate the space with higher dimensional cells, and it's an alternating sum of the numbers of elements in each dimension. Okay, so now, commuting group matrices. I'm going to at least say one theorem that I recently was able to show. So, and it's about commuting matrices. So 2 square matrices commute if their product is equal either way. And I consider this set, which is an n-tuple of elements in G that pairwise commute. Don't worry about that 0 there, but I wanted to. It's just a path component of that space. So you can ask, but this is an algebraic variety, actually. I was forgetting to say, but why? Because it's defined as the equations of the entries of the matrices in G, okay? So this is an algebraic variety, and we can compute its Euler characteristic, or try to compute its Euler characteristic. Why do we care about commuting group matrices? Well, I could say many things, but maybe this is a motivation from quantum physics. Because going from classical physics to quantum physics replaces functions by operators, so matrices, basically, and the evaluation of functions by brackets, let's say. Of course, I'm being very vague here. But the interesting thing is that operators that commute behave classically. So matrices that commute somehow correspond to quantum observables that can be simultaneously measured. So this may be one motivation to study commuting matrices. Okay, so how many commuting group matrices are there over a field of prime characteristic? Okay, maybe now this is another jump, but I can just think of this finite set, numbers from 0 to p-1 as a field, because I can multiply them mod p and add them mod p. This will be a field. And recall that this space is given by polynomial equations, and we found this formula for the number of points in this space up to conjugation. This quotient pi g is up to conjugation. And this is in a very explicit formula. It only involves the Weyl group, which I cannot explain, but it's like also a symmetry associated to the Lie group, and the determinant so this is the characteristic polynomial of the action of every element in the Weyl group. And the other characteristic has a very similar expression. For example, I can just evaluate this determinant and, for example, consider 3 commuting matrices in S of 5. It will be this finite number of points in a finite field. Okay, so conclusions. The Euler characteristic is one of the simple properties of a space. This is at least a concept I want to convey today. But it's also extremely useful. It's related to total curvature counting, surprisingly, and many other global properties. There are also many other refined invariants that I cannot talk today, but they are studied in a master course on algebraic topology, let's say. But this is the most important thing, is that the qualitatively different spaces cannot have the same invariance. So for example, 2 vector spaces, if they have different dimensions, they cannot be the same. 2 surfaces, if they have the different genus or different Euler characteristics, they cannot be the same. And this can be applied also to varieties, Lie groups, etc. That's what I work on. Okay, mystery question. Can one detect curvature by counting solutions of polynomial equations? This is a very strange topic for me, and it's a mystery because curvature is intrinsically continuous concept, whether counting solutions with integers, in integers, is fundamentally discrete nature. So in fact, I don't know the answer to this question. I have no idea, but that's why mathematics research is very important and very interesting to me. Thank you.
So we now move on to the second presentation. So we are moving to geodynamic modeling in tectonics and technophysics. And the speech will be by Filipe Rosas, which is a member of our school council, and is also a member of the Instituto Dom Luís.
So thank you very much for the invitation. I'm going to talk about geodynamic numerical modeling today. And I will concentrate on trying to illustrate the use of this beautiful technique into solving one of the main important problems in present-day tectonics, which is subduction initiation, the way through which subduction is initiated on Earth. So, of course, many of you, most of you probably don't know what subduction is. We will get into that in a minute. And so I will need to convey some basic concepts of plate tectonics. We all know that plate is, the Earth is cooling. So we have different layers in the Earth. The shallower layer, it's the most cold one. It's the colder one. It's also the one which has elastic mechanical behavior. That's where earthquakes occur, of course. And this outer layer of the Earth is subdivided in different pieces. We can see it like that. And each of these pieces we call plate tectonics. And the way they move relatively to each other determine, for instance, the occurrence of most volcanoes and most earthquakes on Earth. You can see there, I don't like to use this because, yeah, there you go, because I'm colorblind and I don't see the light. But on the top right, you can see that the distribution of the earthquakes and the volcanoes mimic the geometry of the different plate tectonics, okay? So we know that when plates drift apart from each other, that's the situation in which new oceanic lithosphere is formed at the oceanic ridges. We can see it here, okay? And so new oceanic lithosphere forms. It is going to push aside the old oceanic lithosphere. So it's this idea that I'm sure you've heard about, the double direction conveyor belt, the notion of seafloor spreading, okay? This is, of course, a geometrical or a kinematical description. And what is really interesting and important is to understand the dynamics of it. That is to say, what forces drive this process. And this has to do with ridge push. So the drift apart, the divergent movement between tectonic plates is driven by, it's actually a gravitic gradient, the collapse, the gravitical collapse of these mid-oceanic ridges that drives this divergence between plate tectonics. Okay, this bears within a very important consequence, which is the one I'm trying to illustrate up there. And it has to do with the fact that younger oceanic lithosphere is, of course, lighter because it's hotter. So it's lighter, it's thinner. And as the distance increases from the oceanic ridge, lithosphere becomes colder, becomes older, becomes colder, thicker, and and stronger, evidently. So to compensate for the generation of oceanic lithosphere, we have on the bottom right the so-called subduction zones. Subduction zones are sites where oceanic lithosphere is consumed. One of the plates dives into the mantle beneath the other plate, and the force that drives this movement is the negative buoyancy of the subducting slab. Okay, so the geometric description coincides. It's all about convergent plates. One is diving beneath the other one, but the force driving the process is slab pull, and this is going to be very important in a moment. Okay, so these are the basic concepts of plate tectonics. Now I would like to call your attention for the diagram on the top right, which I hope conveys the idea that there is a huge difference between the ages of the oceans and the ages of the continents. So if you look, there's a scale. The reddish stuff, it's the youngest stuff. The bluish stuff goes until 200 million years. And if you look at the oceans, you'll see that there's very little bluish things. Okay? Even I, that I'm colorblind, can see that. So that means that the ocean floors are generally younger than 180 million years, but are always definitely younger than 200 and something million years. Whereas the continental rocks are dated with zircons from 3 point something, almost 4 giga-years. That is 10 to the 9 years, okay? So this means that oceans come and go, but continents are always here, okay? So this means that the oceanic floor along the history of the Earth needs to be recurrently recycled, okay? And this general idea was summarized by the concept on the top left, put forward by Tuzo Wilson. Tuzo Wilson was one of the pioneers of plate tectonics. And what he said was that we can look at the lifespan of an ocean in terms of you know, we have a continent. The continent breaks apart, endures rifting. The rifting evolves to an oceanic basin. The oceanic basin matures. But at a certain point, we have to initiate subduction. That's what you see there, subduction initiation, so the ocean can be consumed, so the oceanic floor can be recurrently recycled. So all very good. We have a beautiful theory, plate tectonics, astonishing revolution in the history of the Earth. You know, this beautiful summarizing idea of the Wilson cycle. But the problem is, how can we initiate a new subduction zone? If we put the numbers on that, we'll see, and that's why I was talking about slab pool, that the driving forces of plate tectonics are simply not enough to start a new subduction zone. In fact, they are 1 order of magnitude below what is necessary to rupture pristine lithosphere in the borders of the Atlantic Ocean. So, for instance, if you want to close the Atlantic Ocean, of course, you have to start new subduction zones at the sides, near the margin, at the European margin, at the North American margin. There, the ocean floor is 160, 140 million years. To rupture that ocean floor, you know, to generate a new subduction zone, you need an amount of force that doesn't exist in nature. So you have a beautiful theory, but you cannot explain one fundamental step of this theory. And this is what we were going to model. This is the problem we were set to solve with our geodynamic modeling. So bear with me, I'm going to explain why. So one beautiful paper, one paper by one of my favorite scientists, Robert Stern, just you know, tried to make sense of all of this, and he he established this fundamental difference between what he called spontaneous subduction initiation and induced subduction initiation. So spontaneous is when is the situation we were just discussing. We have to rupture old, very strong lithosphere, and there's not enough force in nature to do so. But induced subduction initiation is when the concept is very simple, and it has to do with the following. Instead of rupturing a new, pristine portion of lithosphere to create a new subduction zone, you take advantage of a pre-existing weakness in the lithosphere. So it's like you are going to reactivate a mechanical weakness which is inherited. So there is a big conceptual leap in assuming this possibility, which is maybe subduction zones were formed at a certain step of the Earth evolution, at an earlier stage where stuff was hotter and hence was less strong. And then it was subsequently always used, that is to say, new subduction zones did not form many times, but they were propagated from pre-existing ones. Here's an example. You have the situation around the Pacific. Everybody knows about the ring of fire in the Pacific, lots of earthquakes, volcanoes. Why? Because all around the Pacific we have subduction zones. In the Atlantic is the opposite. There's no subduction zones around the Atlantic, okay? The boundary between the plate tectonics in the Atlantic is in the middle of the Atlantic, okay? So there are no subduction zones around the Atlantic, but if we accept the idea of the Wilson cycle, one day we can postulate that the Atlantic is going to close, okay? Now it's in the opening phase, somehow it's going to close. So we have to initiate subduction zones at the Atlantic margins, okay? So according to the induced subduction initiation theory, you have to propagate the new subduction zones in the Atlantic from the pre-existing ones in the Pacific, okay? So the induced subduction zone idea, which we are going to test through numerical modeling, and which models I'm going to show you in a minute, is the possibility of this happening. How can you have a jump from a subduction zone from the Pacific Basin to the Atlantic Basin? One possibility is the so-called polarity reverse subduction initiation. Polarity reverse subduction initiation is actually very simple to understand. We have an initial pre-existing subduction initiation from which a new subduction initiation is going to propagate. How? Here is how. So you imagine that I have a subduction initiation, so my hand is subducting beneath this other hand. But attached to this subducting plate, which is being sucked downward because of its negative buoyancy, I have a buoyant plateau. Maybe a microcontinent or what we call a terrain, maybe something else. And this microcontinent or buoyant plateau is going to arrive to the subduction zone. It's going to obstruct it. It's going to choke the subduction zone. And it will, and the conjecture is, it maybe will be capable of bending it downwards, creating a new subduction zone from the original one with an opposite polarity. This is the general concept, okay? So I'm going to show you how did we test it, okay? And we tested through these beautiful, beautiful models. This is the work of a PhD of myself and João Duarte, which is Jaime Almeida, he's right there. We came up, but he put together these beautiful models in which we have exactly what I was discussing. So we have an overriding plate, the plate on top, it's on the left, it has 20 million years, and we have another denser, older subducting plate, which in the left has 30 million years, in the right has 90 million years. It is going to subduct, but note that there is that thing contoured in white, which is a plateau. It's going to arrive to the subduction zone, and it's going to choke it, creating a subduction zone in the opposite direction. So we can see in the first model, there you go. You have the plateau arriving to the subduction zone. Not yet, not yet. There, it arrived, and ping, a new subduction zone is forming in the opposite direction. So why do I think this is beautiful? It's very simple. It's because this is not geometry. This is not kinematics. All the movements that we see here arise from the dynamic equilibrium between the forces that govern what is going on in nature. Those forces are the negative buoyancy of the subducting slab, which are opposed by the viscous resistance in the mantle. So you know when you are rowing, okay? If you are rowing in water, it's easier than rowing in honey or in another viscous material. So you have the negative buoyancy and the viscous resistance, okay? And in these models, all the movements, you can see it here also, are the result of this dynamic equilibrium. So these results, which were published in IPSL and have been highly, highly cited since then, what they show, this is the paper that we've published. I'm a co-author of the work of Jaime, which is more cited, okay? And I have a few papers, but it's very quickly cited because we are showing for the first time that this is viable. This is possible. And this is us here in IDL with our geodynamic modelers. Here's another situation, I'm almost finishing, which has to do with the attempt of overcoming one big limitation of the first set of models, which is they were done in 2D. These ones that I'm going to show you are three-dimensional models. And why is this important? Because if you consider the dynamics of the system, and if you are saying that the system is driven by the negative buoyancy of the slab, you are neglecting the contribution of the negative buoyancy of the slab in the third direction, okay? When you do 3D models, which are much more complex, computational demanding, etc., you can also look into other variables, such as the dimension of the obstructing plateau, okay? And so we were able to show that this is going to take a little bit. Oh, sorry. Something wrong with the movies. I cannot believe this. I tested this before. I hope not. Okay. Let's see. Are they going to appear? No? Oh, here they are. So we see the same set, but now it's three-dimensional. We have the obstructing plateaus, but they have different dimensions. And we were able to tackle more, to gain new insight on the dynamics of the system, because a little plateau in reality creates the new subduction zone with the polarity reversal, and the biggest plateau in this case also does it. But, so even, why is this is strange situation? Because in this case we have a bigger plateau, so the slab pull force of the slab is smaller because we have a bigger dimension of the subduction being obstructed. So just to conclude, I want to say that the main result that we've obtained here was to show that this polarity reversal mechanism of initiating new subduction zones, it's, given our results, it's not only a possible means of creating a new subduction zone, it's actually what you would expect. It's a probable way of doing that, okay? And That having been said, I just want to, and this is my last slide, I just want to talk about future work to say two things. I think that geodynamic modeling, it's a beautiful tool, but it does not exist beyond the geological and geophysical knowledge. So you have to know about nature. Models have to be rooted in the knowledge that you have from the natural system that you are studying, okay? And these are all examples of the group, of works that are done in the group. I think we have two future directions. One is a more integrated Earth systems vision in which we combine the internal geodynamic modeling with the consequences in terms of the external geodynamics of the system. For instance, we have to be able to tackle, and some groups are already doing that, how does the creation of orogens, the orogeny, the topography on Earth, influences the circulation of atmospheric circulation and the climate. So a more Earth systems integrated view, I think, will be one of the future ways to pursue. The other, of course, is to take advantage of the beautiful, enormous amount of data that are coming from the NASA and European ESA from other planets in our solar system. You have to know geology. You have to know how to recognize the geomorphological patterns, how to recognize the tectonic and structural patterns, and at the same time, you have to know how to use geodynamic modeling. This is the beautiful team of geodynamic modelers in IDL. We have strong collaboration with both Nicolas Riel and Walter Scheller, which are in Mainz, Germany, and in the VU Amsterdam, Netherlands. And then we have a beautiful group of PhD, a very promising group of MSc students doing brilliant work. This is essentially our work, and I want to thank you them and to thank you for the opportunity. Thank you.
So now we move to the presentation of Ana Sofia from CQE, the Center for Structural Chemistry, and she's going to speak about from biomass to nanoporous carbons, key materials to face water contamination with pharmaceuticals.
Thank you, Professor Margarida. Good afternoon, everyone. I must start by thanking the opportunity to present the work that I've been developing about the transformation, valorization of biomass to produce nanoporous carbons. The problematic of pharmaceuticals in water is a global problem that calls for improved water treatment technologies to face it. Recent literature addressing the comparison between conventional and advanced water treatment processes identify activated carbons and ozonation has the most promising available and consolidated techniques to face this type of problem. We can look to the example of Switzerland. It's a full-scale demonstration of this reality. It's already mandatory by the Swiss law to remove 80% of the contaminants of emergent concern, including pharmaceuticals, that are detected in the influent of the wastewater treatment plants. For this, they are upgrading their treatments using, in the ones already in service, more than 50% of them use activated carbons. In those plants or under construction, the percentage of those that selected adsorption onto activated carbons is even higher. Activated carbons and nanoporous carbons is exactly the same thing. The last name is only more recent. And these are solid materials that are composed of carbon atoms that are arranged in graphite-like microcrystallites that are organized randomly and create spaces between them. These spaces are the nanopores, so that's why the name, and they are divided in micropores when the dimension of the aperture is lower than 2 nanometers, and these are the adsorption active sites, and mesopores, the slightly larger ones that behave as transport pores. Besides this carbon skeleton, these materials also have heteroatoms like oxygen or nitrogen that can tune their surface chemistry to a basic or acidic surface chemistry. I'm speaking about area. I will tell you that today, in my hands, in this flask with some grams of activated carbon, I have the area of a football stadium. This is what we have with activated carbons. Regular ones have 1,000 square meters per gram, but they can reach 3,500 square meters per gram when we produce them in the lab, controlling the conditions. This brief introduction is to lead you to the projects that we have been developing. They are built based on a circular economy principles. So we are using biomasses or byproducts of industries that are available here in Portugal. We have been addressing a lot of biomasses, and the green chemistry and sustainability is also assured by using activation methodologies that are scalable and viable economically. These materials are being benchmarked against commercial activated carbons for the removal of pharmaceutical compounds. And with all the information, the lab scale data that we gather, we developed a tool to identify the key parameters of the players, activated carbon, pharmaceuticals, and water that will allow better performance of the pharmaceuticals to face these problems. It's impossible to work with all the pharmaceuticals that we have in the water, so we have to select some. We selected 3. Sulfamethoxazole is an antibiotic. Diclofenac is an anti-inflammatory, is the active principle of diclofenac. Probably most of us, Voltaren, sorry, most of us already used it. And carbamazepine, that is an antipyretic and psychiatric drug. These compounds have dimensions that are lower than 2 nanometers, so they will be able to diffuse until the adsorption active sites. They also have different hydrophobic and hydrophilic properties and charges. They are all detected in wastewaters in Portugal and worldwide. And why? Because the conventional water treatment is mainly based on a biological process. This biological process relies on microorganisms that will feed themselves on the organic matter that we want to degrade. But the problem is that pharmaceuticals are resistant chemical compounds that are built to have biological activity and to resist to degradation. So some of them still remain after this secondary treatment. So we can add activated carbon in this stage, in the secondary treatment. For that, we will use this type of water that we collect in the reactors, or after the treatment, and we will use secondary effluent to mimic this type of conditions of application of the activated carbons. Today, I will focus mainly on the byproducts of pine nut production, because these were the most promising biomasses we studied so far, pine cone and pine nut shell that I will call by PNS. We developed a set of activated carbons. I will tell you that the PNS-derived ones obtained by steam activation are the better ones. They reach BET areas higher than the commercial carbons and than the ones prepared from carob or from pine cone. So they were promising for this type of application. To do this type of tests and to be able to build the models, we need to do tests with different types of water, with the water that only has the pharmaceutical compound and has no organic matter competing, and also real water, in this case, water that was collected in 2 wastewater treatment plants, one in Beirolas near the Vasco da Gama Bridge here in Lisbon, and the other in Faro Noroeste. The waters all have similar pH and electrical conductivity to maintain some of the parameters. In these isotherms, I will not explain them totally, but what I want to highlight that when we move from a single solid condition to a multi-solid condition, the adsorption capacity decreases greatly for all the pharmaceuticals. Other important message, the PNS77 steam activated performs similarly to the best commercial carbon that has a mineral origin. Similarly for carbamazepine and diclofenac, and is better for sulfamethoxazole. The trend between the pharmaceuticals is associated with their hydrophobicity. Higher the hydrophilicity, the less prone they are to be absorbed by the activated carbons. Activated carbons are non-specific adsorbents, so they will remove the target compounds, in this case the pharmaceutical compounds, but also organic matter that is present in the water, and in this case we proved that the carbons behave, these carbons we developed in the lab behave very good for our targets, but also for the other organic matter that is present in the water. With all the experimental data, there were built models that allow us to preview the removal of the pharmaceuticals at their natural occurring concentrations. So if we decide to add 10 milligrams per liter of carbon, 10 milligrams of carbon per liter of water, we see that with the pine nut shell, we get better removals than those obtained from the material that we prepared from carob waste. We had very good results with the materials we prepared by steam activation here in the lab, and we established a collaboration with a company in the United States to upscale our synthesis protocol, in this case using CO2 activation. What I have to share with you is that we succeed. They were able to replicate the textural properties of our materials, and the major difference is associated with the particle size. The material that was prepared in the company has smaller particle size, a larger fraction of particles with smaller particle size than the one we prepared in our lab. And this material was even better than ours. We see it removes more of the pharmaceuticals here, also behaves better for the organic matter removal, and this is because since we have smaller particle sizes, the diffusion until the active adsorption sites is facilitated. We had, during these projects, we gathered a large number of experimental data, and with this we built a model to identify the key parameters of the activated carbons, pharmaceuticals, and wastewater that will allow us to improve the performance of these materials for this specific application. The selection of activated carbons for full-scale water treatment is a challenging process, time-demanding, that requests experiments in the lab with the specific carbons that we may select and with the specific water that we want to treat. This happens because the number of pharmaceuticals is enormous. Because regarding the carbons, there is a lack of information in most of literature. Only usually BT area is mentioned, and it's not the only parameter that is relevant. We need studies with the wastewater because we need to have the competition scenario. And there is also a problem associated with analytical chemistry because we are speaking about very low concentrations, ppbs or ppts, and these request very heavy analytical work. We gathered 7 activated carbons, 3 pharmaceuticals, and 6 different types of water, all of them characterized properly. And we identified some correlations in univariate analysis. We see that there are relations between the removal and the BT area, or the volume of larger micropores. And regarding the pharmaceuticals, there is a relation with log D, that is a coefficient, a partition coefficient, that is a measurement of the hydrophobicity of this type of molecules. The multivariate analysis clearly shows that the biggest relevance is for the pharmaceuticals. In fact, they will be the ones that affect the more the performance with solvation energy and, once again, log K, OW. Regarding the carbons, BT area, density and volume of larger micropores are relevant parameters to preview the performance of this type of materials. Has remarks. In fact, PNS, pine nut shell, is a very promising biomass for this type of application. It allows to obtain high-performing activated carbons that will allow to use lower doses in practical applications for wastewater treatment. Regarding the pharmaceuticals, higher their hydrophobicity, higher their ability to be absorbed onto the activated carbons. And this is regardless the type of water and the type of activated carbon that we are using. We have an ongoing project with the same biomass, now with controlled particle sizes and aiming drinking water treatment. We maintain the previous target compounds and we add some new ones that are relevant for this type of application. since we have different dimensions of the particles, we are addressing different technologies. And another important task of this project is the regeneration that allows us to reuse the same material again and reduce the amount of biomass that we consume, and also the energy and the amount of residues that we will create. Of course, this is a teamwork. I start by thanking my colleagues here from Faculty of Sciences, Professor Ana Paula, Marta Andrade and Miguel Masqueiro, my colleagues from LENEC that came to hear me today, Maria João Rosa, Rui Viegas, Elsa Mesquita. Their engineering background and great knowledge on water treatment processes at full scale is fundamental for the success of our works, and also our colleagues from United States, Lady and William. This line of research was already recognized with some prizes, two in 2019 and one recently to the new project in 2022. I have to acknowledge funding for the projects, for my research contract, and for the companies that provided the biomasses and the activated carbons. And thank you all for your attention, calling your attention to this need, this sixth goal of United Nations 2030 Agenda for Sustainable Development that calls our attention to the need to offer clean water to everyone. Thank you.
A minha ciência é descobrir novos animais. Experiências.
So it's time to coffee break. We will meet here again in 20 minutes. Thank you. So welcome again. The scientific program will continue with the co-acting basic and applied science. I'm asking again to Professor Margarida Santos Reis to present the next Professor Hugo Ferreira.
Yes. Thank you very much. So now we move to a different research unit and to a different area. We are still going into physics, more clearly biophysics, and Professor Hugo Ferreira is going to speak about the nano-world. Thank you very much.
So good afternoon to you all. Everybody feeling happy? Perfect. So let me kind of start by putting my gear here and tell you that actually, doing science is much like cooking. You pick up an old recipe, you follow it, then you taste it. Then you figure out that maybe this could have something, a bit of this and of that. You hypothesize that combining these different ingredients will help you boost the flavor of the recipe. And then you roll up your sleeves, you go to the kitchen, you work hard in the pursuit of your signature dish. Okay? And this is why I brought my lunch bag. Okay? So what can we find inside? Actually, I was cooking early this morning a wafer. And what do you see here? Gold. You can recognize the glow. And this is what we are going to talk about today. Okay? So my name is Hugo Ferreira. I work here at the physics department, at the faculty, and I do research at the Institute of Biophysics and Biomedical Engineering. And today I'm going to present you a tale from the nano-world. My precious. How can golden flames defeat evil? You know that gold, this special element, has been through the ages considered both a blessing and a curse. Since ancient times, it has been a symbol of value, of status, and of power, but also of ingenuity, of beauty, and of the divine. And finally, of love and madness, maybe two sides of the same coin. So today, I'm actually telling you about gold as a symbol of hope. Gold has found throughout the ages a number of different applications in medicine. And in particular, addressing a number of purposes and ailments. For instance, the earliest applications of gold have been as a prosthetic. And today, even in dentistry, we are using gold. But not only that, for instance, in 1890, Robert Koch found out that actually gold could curb the growth of Mycobacterium tuberculosis, so as a treatment. But not only that. Nowadays, gold is being used for diagnosis. But much more, it has been used or tested and used for a number of treatments ranging from cancer, rheumatoid arthritis, and even malaria and HIV. So it has actually anti-inflammatory properties. So gold is special. And of particular interest to us is this gold in a nanoparticulate form. At these small scales, nanoscales. And it has been finding a number of different biomedical applications in vitro diagnostics, in imaging, in radiotherapy, in brachytherapy. And this is where we are, at the nanoscale. But why are we so interested in these minute sizes? Well, it's because the nano realm is strange. Suddenly, at these scales, things start to behave in unexpected manners. And the nano is actually in the middle of the classic and the quantum Earths. How come? Not only the element matters, but size matters. And as we go down in dimensions, a solid can suddenly behave like an atom. Not only that, also shape matters. And in particular, gold can take different shapes of color. And we can use that in our advantage. In fact, if we remember of the divine, in the Middle Ages, artisans producing stained glasses were actually the first nanotechnologists. Unknowingly, they were manipulating matter at the nanoscale, producing these various different colors. So gold can find different applications. And at IPEB, we are particularly interested in applications in oncology. Okay? For instance, in the presence of cancer DNA, actually gold becomes royalty. Let me go back to my lunch bag. So actually, when gold is isolated, it is in this nanoscale, it's not bright yellow, it's actually red. But in the presence of cancer DNA, it becomes blue. Not only that, we are looking at gold nanoparticles for photothermal therapy. And in practice, if gold is blasted with near-infrared light, then it can purify cancer by fire. And this is what we have been developing, applications in oncology for photothermal therapy, and this is actually a truly multidisciplinary, multi-institution collaboration, which pleases me a lot. And our end goal is to develop novel theranostic solutions, test them in experimental models, and then translate them to cure some of the most common and deadliest cancers, such as breast, such as, for instance, melanoma or thyroid. Some of the cancers that are most difficult to treat. For you who don't know, theragnostics means both doing diagnostics and therapy, and this is what gold enables us to do. We started by developing novel, sustainable, and environmentally friendly formulations of gold nanoparticles. And for that, we made use of a natural compound called rosmarinic acid. And then we tested it. You can see that actually different sizes of nanoparticles, they absorb light preferentially in different wavelengths. So we can have excitation both in the visible and the near-infrared range. So we tested it with a laser and confirmed that actually particles absorb such light and heat up. In 3 minutes, you can heat up over 5 degrees centigrade, which is enough to heat up a tissue, and if you leave it a little bit longer, to kill it. And this is what we did next. As you can see here, this is the tumor, an animal model, mice, in which we inject this nanoparticle formulation, and after 5 minutes only, the tumor was necrosed. And this is kind of unheard of with other chemical or physical therapeutic approaches. Given the promise that we have, having this very efficacious solution, we are now taking the next steps. How can we make this actually more secure and translate this into more clinical practice? One of the side effects that we saw is that may happen some skin burn in the tissues around. But we can avoid this. For instance, making use of aerogels. And again, we took this approach of using sustainable and environmentally friendly materials, and we used pectin, which you can derive from fruit. And actually, it can make a pretty good aerogel, both thermally insulator, light insulator, biocompatible, and low weight. This is where we are at, and kind of as a final message to you, I'd like to say that when we are looking the evil in the eye, we should take action, fight back, and foresee a brighter future. And with that, I'd just like to acknowledge the work from Tânia Ferreira Gonçalves. She is actually one of our students from biomedical engineering and biophysics, an exceptional PhD student. She's being co-supervised by me and Catarina Pinto Reis, our colleague at the Faculty of Pharmacy, and as well as IBEB. This is also the work from João Pinto Coelho at IBEB and LOLS, and a number of other colleagues here at the faculty also are contributing to this project, as well all rodents. With that, if you're interested in knowing more, please feel free to contact me, and thank you for your kind attention.
Many thanks, Hugo, for the interesting talk. And now we are moving to a different topic. We are going to go into conservation biology, and I invite Maria Dias from the C3C that is going to speak us how to use tracking animals as a tool for conservation.
So thank you very much, Professora Margarida Santos Reis. Thank you also for the very kind invitation to be here today talking about my work. And now that I'm in the thank you part, I will take the opportunity to acknowledge to all the co-authors of this work. They are many. The work that I'm going to present today, in fact, is the result of a large-scale collaboration of many researchers. And what do they have in common, or what do we have in common, is that we have been studying migratory seabirds in the Atlantic using tracking data. So the dots that you see in this map are, in fact, important colonies of seabirds in the Atlantic. And just to start by explaining what do I mean by migratory seabirds, I will give you two examples. Maybe, well, the first one is a bit an extreme example, is the Arctic tern, is an incredible species, in maybe a biased opinion, of course, but the Arctic terns are famous because they hold the record of the longest distance migration in the planet. As you can see, they can travel 80,000 kilometers per year from their breeding grounds in the Arctic to the non-breeding grounds in Antarctic and back. But we have another example that probably many of you would know, is the Carriço water. For those that have been to the Azores, I'm sure that you heard them, quite noisy. They are also incredible migrants. They can travel about 40,000 kilometers per year in a kind of 8-figure migration that basically follow the wind patterns in the Atlantic. And now to explain a bit what we mean by tracking data. That is the kind of data that we collect using these very small GPS devices or other kind of devices, not nano, so not so small as the kind of stuff that we saw in the previous presentations, but still very small. So the GPS is, we usually deploy, we attach to the feathers of the birds, to the back feathers, as in that albatross, or sometimes to the tail feathers. And the other ones that we use are the geolocators. I will not explain in detail how they work. We usually deploy them in the leg of the birds, and they are quite useful to study large-scale patterns of movement. So this is typically the kind of data that we collect in this case with geolocators. This is an example of this Carriço water was tracked from the colony of Selvagem. We have been studying this colony for the past almost 20 years. And basically what we obtain is just 2 positions per day. That is enough to study these kind of long distance movements. If we want to understand a bit better the small scale movements, we use those tiny GPS devices. So basically this, and again, an example of a Carriço water from Selvagem. During the breeding season, they go and forage along the coast of Africa. If we start tracking several individuals, we start seeing kind of common patterns, and we can start identifying important sites at the population level. So seabirds, I will not spend a lot of time also explaining what seabirds are. Last year we had an excellent presentation from José Pedro Granadeiro talking about seabirds. Just to say that there are about 360 species of seabirds in the world. They are not a unique entity in terms of taxonomy. They belong to different families. Gulls, everybody knows gulls are seabirds, but also cormorants, penguins, auks, and of course albatrosses and shearwaters. So they are not a single kind of taxonomy entity, but they have in common the fact that they are both terrestrial and marine animals. So as all birds, they depend on terrestrial habitats to breed, to lay the egg and to raise the chick. Usually in case of seabirds, they breed in islands. But they also depend on the marine systems to forage, so they find the food that they need to survive in the marine environments. And just to say that usually when we think about marine species, we don't think about birds, but in fact seabirds are very important in marine food webs. As we saw before, they are highly migratory. Many of them are highly migratory, so they are able to move very long distances. And because of these two traits, they are in fact really global connectors. Nowadays it's quite fancy to talk about connectivity. We see connectivity everywhere. Seabirds know very well what is connectivity. They connect very distant regions, but they also connect very well terrestrial and marine environments, probably like no other group of animals. They are unfortunately not in a very good shape, let's say, in terms of conservation. If we compare seabirds with other groups of animals using this red list index, that is a metric to measure the probability of a group of species to survive in the wild. So we have the corals that, as you can see, I mean, this is a measure over the time. Corals, as we saw also in the morning, unfortunately are not doing very well. But birds, in fact, in general, as a group, are not so endangered. Especially when compared, for example, with mammals and with amphibians. But within birds, if we see only the seabirds, they are almost as bad as amphibians. And for the biologists, they probably know what that means, because amphibians, in fact, they are known for one of the group of animals most in risk of extinction. And why is that? So I did a global review a few years ago about the main threats to all seabird species in the world. Well, we found that 1/3 of the species of seabirds are globally threatened with extinction. About half of the species are suffering population declines. And why is that? Because on average, each species of seabird is impacted by 3 different threats. And these threats are mostly bycatch on fisheries, invasive species in their breeding colonies, overfishing, climate change, hunting, disturbance. So these are the top threats to these species. And as you can see here, and also in this image, we are talking about threats that impact both the marine and the terrestrial habitat. So basically, well, because they are both terrestrial and marine species, they are all also suffering from the impacts that we are causing in both environments. But I don't have only bad news, so some good news. They are relatively easy to study, especially compared with other marine species. And especially to study the movement that they do. As I was explaining before, these kind of tracking devices were in fact, the development of those devices was a game changer for the study of these species. And about 10 years ago, we saw lots of studies being published with the results of the studies of the movements of seabirds. So you see here the Carriço shearwater and the Arctic tern, but many other species in the Atlantic, and the results of the studies. And what all these studies started to show is that they were almost, or many species in the Atlantic were targeting a specific area in the central North Atlantic. You see that area that I'm showing there. Even species, for example, this sooty shearwater, I don't know if you can see the pointer, the sooty shearwater, this species here and this species, they are coming from the South Atlantic, so very, very far away. The South Polar Skua is coming from the Antarctic Peninsula all the way, they migrate all the way to the North Atlantic to spend the winter in that region. And so we decided to investigate a bit why and what was happening there. So we started this massive data compilation. We've collected the tracking data for the species that we had some evidence that could be using that region. We're talking about 23 species from more than 100 colonies and more than 2,000 individual birds tracked. I will not explain in detail the data analysis because it takes a lot of time and I don't have that time, but just to say that it was a method that we developed, not for this study, but was also, well, I was part of that work to develop this method, and we later on published this method in the format of an R package that we call it track to KBA, that means track to key biodiversity areas, and we tested this method with other species. So if you have curiosity, we published also last year this R package. So moving on to the results, the interesting part, so what we found was in fact the existence of an incredible hotspot for migratory seabirds, so located northwest of the Azores, around 1,000 kilometers northwest. And we estimated that the site is used by between 3 million and 5 million birds, depending on the season. So it's quite a very extremely important hotspot for migratory species. We found that 21 species of those 23 that we analyzed initially, 21 were using this area, and from very different taxonomies, again, from 5 species of shearwaters, 5 species of petrels and fulmars, the skuas going there as well, auks, almost 4 million auks we estimated are using that area, and some gulls and terns as well, including our famous Arctic tern. During that long distance migration, they stop there to forage, like, well, just for a stopover. Just for curiosity, from Portugal, we have 5 species going there. I will just highlight the last 2, the Xenos petrels and the Desertas petrels, because they are endemic from Portugal. They only breed that means that they only breed in Portugal, in Madeira, so nowhere else in the world. And they are quite special. They are highly endangered with extinction, and they are quite special because they go there not during migration. So they go there during the breeding season. That means that while one individual is staying in the nest, taking care of the chick or incubating the egg, the other one goes to that area, so travels the entire Atlantic, crosses the Atlantic and comes back. In the same way we go to buy food in the supermarket, they do this incredible trip to cross the Atlantic. Well, and the result of this work, in fact, led to the creation of a marine protected area that we call the NACES. And it is important to say that this was done in collaboration, in close collaboration with the OSPAR Commission, who manages this region of the Atlantic. So the creation of this MPA, of course, was done, well, was driven by this study, but was in fact in a collaboration with the OSPAR Commission. And it is the first protected area of this kind that to protect highly migratory seabird species based on tracking data. Is one of the largest MPAs, marine protected areas in the world, and is located in the high seas. That was quite also an important step because, well, as some of you probably know, the discussion about the protection of the high seas is a very active discussion because currently the high seas are kind of no man's land or no man's sea. Is beyond any jurisdiction. I was very happy also to say to know that the declaration, the final declaration of this area was during the OSPAR meeting that was in Lisbon. That was a coincidence and was last year, the 1st of October, but in fact I should say, quite happy to be in Lisbon because could be in any other place. By chance was in Lisbon, so I was happy for that as well. Why are the birds going there? We don't know exactly for sure, but we know that they are going there to forage and to find food, and we believe that this is linked to the abundance of mesopelagic fish. We have evidence also from tracking data that many other species are also going there. Sharks, tuna, cetaceans, and sea turtles are going there. So if you want to well, read a bit more about this, we published the results in this paper. Multi-species tracking reveals a major seabird hotspot in the North Atlantic. We published also another study to share also this political experience and the opportunities and challenges of using tracking data in the conservation of the high seas. And again, we hope that this can help in these current discussions in the United Nations to protect the marine biodiversity of areas beyond national jurisdiction. This work was only possible thanks to the existence of this database, the seabird tracking database. I was managing this database at the time. I was working, not here yet, I was working in BirdLife International. But basically, this is a massive collaboration of scientists that share the data in a single database that can be used for conservation. So just some conclusions. In conservation, as in many other fields, but in conservation is particularly important, I think collaboration is absolutely key. We tend to work with our species and our study side, but it's fundamental to see the big picture and to collaborate to be able to progress. Data sharing is also extremely important, and again, it's sometimes is a tricky issue. We are afraid of losing our data. It is expensive to collect, but at some point, it is important to share the data for a wider use and to use in these other ends, let's say. And finally, to say that, and a bit about this discussion about fundamental versus basic and applied science. This work was only possible thanks to the curiosity and all the fundamental science and ecological studies and behavioral studies that were done initially. That was kind of what guided us to understand that was something going on in that region, and then led us to do this study. And I started with the acknowledgement, so I can finish with an invitation. So there's an exhibition now in Museu Nacional de História Natural e da Ciência about this kind of birds. It's not an output of this project, it's another project led by Dra. Mónica Silva, also from CFTC, but it's a nice exhibition. I helped a bit, so I invite you all to visit the exhibition and take an opportunity to visit the museum as well. It's very beautiful. And let me thank you for your attention. Thank you.
And we now move to the last presentation of the day. I hope, because I will not speaking after this, I hope that this session was able to show you really the excellent science that we do in such a diverse number of topics. And this is, remember again, is just a very, very, very small sample of what we are able to do in Ciencias. Recall the numbers, 700 projects, 1,000 publications, so we could spend weeks speaking about our science. Next year, more news will be coming for you. Thank you very much for your attention. And now, History and Philosophy, Ana Duarte Rodrigues, that is going to speak to us about building bridges for the history of science. Thank you.
Okay, thank you so much. So we are getting to the end of this great day of sharing research. And I also thank you for this opportunity to talk a little bit about building bridges, some examples that I have already made, but also some about the future. So let's start by talking about the Aqua project. This was a historically driven project, but with other fields of knowledge of exact and natural sciences, mostly landscape architecture and urban studies, but also hydraulic engineering. And it was a joint venture with the technical university. So my co-PI is an hydraulic engineer, professor at that university. And we have reached much further than we would do only with historical knowledge. And this is the kind of example that I want to talk to you today. So we selected, so the idea is to show the efficiency of water management in the early modern period. This is the idea. This is an idea that I have for the past 10 years. If quintas, if our estates, farms and villas were self-sustainable, something has to be there. If they were self-sustainable, it's because sustainability was there. So they were used to reuse water. Everything that is our motto today, that was their daily reality. So we have selected 4 case studies. 2 of the civil context, 2 of the religious context, 2 big scale, 2 a short scale. So we have the Royal Palace of Queluz, the Convent of Christ, and then the Quinta da Princesa and the Convent da Rábida. In all of them, the conclusions are more or less the same. Of course, the technological apart at the Royal Palace of Queluz is a little bit different, or the Convent of Christ. We are going to see why. Okay, so this is the methodology. So we have used multi and interdisciplinary methodologies. And when we are talking about interdisciplinarity, this is the reality. This has happened between me and Didier Kovachov, between me and hydraulic engineers. this is not, it's nice to have a lot of disciplines. No, we work together, and we have reached different conclusions because of that. Okay, so we have the classical historical knowledge, treatises. We have studied a lot theoretical ground, something also that an idea that has fallen apart, that there was no theoretical ground, everything was empirical in Portugal. Is it? I have to recall the first class here in Ciência in Portugal, and there were a lot of students, some of them from the Technical University. We are always talking about the scientific, that Portugal has a scientific backward, so we are quite late regarding other countries. Well, not in the period that I teach. Not, you will change completely that idea. And this is also important. That's why history is so important. It changes the perception that we have about ourselves. So we have all these maps. So the landscape architects, my brilliant landscape architects that do these maps, the survey of all the hydraulic structures, and then the pilot experiments that we are we were able to develop at the water lab. But also we also used a lot of mathematics, and mathematics took me to another level. I'm going to show you how. Okay, so these were the main axes that we studied in this project, like Tomar. Well, we have a lot of novelties about the Convent of Christ and about the hydraulic systems in Portugal because of that. We have also a lot of novelties about clean energy in tide mills, in water wheels, and now that are using, and that the Companhia das Águas de Portugal is interested in this business. So in fact, a historically driven project that will, in fact, are we going to register a patent? I think we will. So it's unbelievable. And also we have a lot to say about the evaluation of hydric and energy balance at Queluz, okay? So, I can say that about water technology, Portugal is at the forefront in the early modern period, in the first decades of the 16th century. And why can I say this? Because in fact, there was this previous idea that early modern hydraulic systems functioned only by gravity, so as a continuous flow of water from the higher level to the lower level. And everything would work like this. Well, there were already pumps here in the Iberian Peninsula used by the Romans in mines. And they are these archaeological artifacts. They are in some museums. And we also know, me and my colleagues that study these kind of things, that pumps are mentioned in gardens, but in the late 16th century. Okay. The study, the transcription of a 500 folio about the expenses of the Convent of Christ between 1535 and 37 has just shown this. Pumps. Pumps were being used there and quite normal. They are not mentioned as something special. So the technological apport in this kind of places, very connected with the crown, very close to the crown, because then we have found other documents from the Queen's Garden of Paço da Ribeira from 1527, where they also were using pumps that were coming from the shipyard Paço da Ribeira das Naus. So it is all connected with the maritime expansion and the great discoveries, okay, that is pushing Portugal to the forefront. The pumps were used in boats to extract water that, because of the leaks, as it was constructed by wood. Okay, so the previous idea is wrong. Another thing, the Convent of Christ is the most sophisticated system that, well, in European terms, one of the most. And why is it? Well, let's just talk about grey water, something that everybody thinks that when we are going to do now more sustainable things, we are going to reuse grey waters. Well, that was normal in the early modern period. But at the Convent of Christ, there is a 4-storey building just to treat, oh, sorry. It's this, I would like to point this. Just to treat sewage. And so these grey waters were mixed with vegetal manure and animal manure, and then all these liquid was channeled into vegetable gardens and into the fields. This is really reused water. Okay, so there's nothing new under the sun. And then, well, let's talk about aquaculture, pisciculture, also here. Well, with a much beautiful design, but this was for fish. Okay, so theoretical background. So it circulated in Portugal. This idea that everything is empirical, that, well, Didier Covas, when she first went with me to the Convent of Christ, she said, no, this cannot be done without mathematics. It's not possible. So empirical, that everything is empirical, just like a master that knows how to do things. It's not possible. Okay, and so we have, in fact, research treatises on hydraulics, on water management, on rivers management for navigation and irrigation. And in fact, we found dozens of books in our libraries from the ancient funds and more. Now, something that will, now, they would not read the books. No, there are editions of translations into Portuguese. So nobody makes translations. They had to sell the books just as we do today, okay? So all this is in our site. So you have all the books, all the editions, all the translations are there. Another wrong idea. Okay, so more sustainability, clean energy. This is one of the most important pilot experiments that we have done. And so we have these water wheels. Well, I'm not going to talk here about all the models and how they were used. It was one of the most important source of energy, way of making energy, of creating energy since ancient times, up until the 19th century or late 18th. But in fact, the idea that, and then now they are doing this, they are doing this at the Water Lab because they are evaluating, measuring the kind, the energy that in fact the water wheel of Mochão would produce. Not much. But the fact is that it is a clean energy. And so it should be mixed with other kinds of energy. But that is already the idea. It's not a novel idea. It's not a novel idea. So in fact, some engineer from the 19th century and also the Nabantina in the beginning of the 20th century, they were all already doing this. So the idea of mixing, still taking advantage of these traditional ways of producing energy maybe is something key for the future. Okay, so now each drop counts. This was early modern reality. This is not new. That was the time when, in fact, each drop counted. And so now here we have, this is the work that I have done with Didier, really close. And so history has given the data, okay? So we took advantage of the restoration works that were being carried on at the Palace of Queluz, at the Gardens of Queluz. Well, we gave all the manuscripts, even books that will say how the jets of water would work, everything. And they were able to estimate numbers for this, okay? Something that we go to a public park nowadays and the water meters gives us all the numbers, all the consumption of water. For this, we had to create the numbers. Of course, there are descriptions also about how high would go a jet of water. So, and based on that, they can also calculate the pressure, also the volume. So they could calculate all there is now a thesis published in English on this. So they could create the values, and then we compared with two other gardens that we already have the values. So we compared the consumption of water in the Royal Palace of Queluz with the Parque Carmona in Cascais and the Parque Valdelobo in the Algarve. And I have to tell you, the gardens of Queluz are, in this reality, in this universe, the ones that spend more water because they have more jets of water. Okay, and now you are all guessing, as I am so happy. And oh no, sorry, you are all guessing. So even with water sense, sprinkler irrigation, drop by drop irrigation, okay, the winner is the Royal Palace of Queluz, okay? So in fact, And all my colleagues were saying, oh no, with the smart system, Anna, no, the consumption of water is less. Yes, less, but not less than historic gardens. And why? Something that has to do with my other project, the Sustainable Beauty for Algarvian Gardens. Why? Because contemporary design just uses too much lawns, too much grasses. And that is not sustainable in a climate as ours. And so, in fact, it's because the problem is the choice of species. And in a historic garden, you only have trees and shrubs that are completely adapted to our climate, so that they live with rain. Enough. It's enough. Okay, so 3 main ideas that have fallen apart. The systems worked exclusively by gravity, wrong. Contemporary choices of garden design are more advanced than those from the past, wrong. Consumption of water in traditional systems fosters more loss of water than smart systems, wrong. Okay, this is why it is so important to use history and history of technology and history of science for future decisions and future technology. Oh, no, sorry. Oh, shit. Okay. This is my team, my super team, the Aqua team. We could not reach this far without you. I am so, so grateful. So not only because you have done an amazing job, so this is the Aqua team, but above all because, well, it counts that you are outstanding researchers, but above all because it has been such a joy to work with you for the past 4 years. And now I have to compare something. All my colleagues, they have mentioned the team, and they have put more or less the photographs like this, so the individuals. But I have another slide showing that we have been building bridges with each other, and that is also very, very special. And that's why the Aqua team became the Aqua family. Thank you so much, okay? Now, one last word to Professor Margarida Santos Reis. I want to special thank for this day, Ciências Day, because we get so acknowledged of all the research that is being done here. Because of this day, last year, I started to build bridges with a biologist, a famous biologist, more or less famous already here, which is Andrea Figueiredo. So I think, and also with Rita Cardoso, Lisette Souza, Alison Benson. Well, we have already something going on, but I do believe, so we are thinking about rescuing grapevine varieties from the past, establishing the correspondence with the help of classical ampeleography, and also then, well, doing a database with all this information, and also studying the projections for climate scenarios in the past and in the future. Well, we have this crazy idea, but although this is already going on, I do think, I have this strong belief that we can go much further in establishing bridges between history of science and other fields, okay? And so, in fact, I do believe that possibilities are unlimited, okay, at Ciências. Thank you so much.
So thank you, Professor Anna. And we have reached the end of our contributions foreseen for this year's at Ciências Research Day 2022. We would like to thank all the participants and congratulate you for all the work produced that makes Ciências ULisboa proud. We will now be closing the Ciências Research Day 2022 with words from Professor Pedro Almeida, Vice Dean for Image, Communication and Institutional Relations. Thank you.
Thank you, Raquel. Good afternoon, everyone. So it's my task again to close this research day, and it has been, I think, a day where we have witnessed excellent science once again, produced by some of our most distinguished and remarkable scientists, some of them among the top 2% of most cited within the world. But also we had the enthusiasm of younger generations, which are eager to learn and to participate in the knowledge about nature. A bit more about nature is always something good to pursue. I must tell you that I was for weeks wondering about what to say to you in this day. And I can tell you that for sure the inspiration failed me this year. And throughout this voyage that I had to find out what to say, I thought about presenting you some gibberish related to the selfishness and the generosity of being a scientist. For example, the kind of words that would point out how scientists can, at the time, pursue and compete in sometimes obsessive quests on behalf of their own self-knowledge, while offering a significant part of their personal efforts and some of the best years of their lives for the ultimate benefit of mankind. Then I wondered if a tour through the Ig Nobel Prizes, you probably have heard of recent years would make you laugh. For example, by telling you that apparently mathematics may explain why success most often goes not to the most talented people, but instead to the luckiest ones. Apparently this gave the prize in economics in 2022. Or that we can use fluid dynamics to probe one of the most puzzling questions in the universe. You may ask what it is. Can a cat be both solid and a liquid? And this was a prize of physics in 2017. But at the end, I took final inspiration from music, as I often do, in fact. And in a way, this is my strategy of going away from difficulties of life and to gain some comfort. And I'm sure that most of you that do research also do this. So I wanted to close this session with a musical tribute to all Ciencias researchers, and in fact, to all researchers. And probably you can recognize these words from very well-known music. I will read them for you. So close, no matter how far, couldn't be much more from the heart, forever trusting who we are, and nothing else matters. Trust I seek, and I find in you, every day for us something new. Open mind for a different view, and nothing else matters. I think this brings a lot about what is doing research. And I invite you all at the end of this very interesting day to take a deep breath, relax, and appreciate how research can be close to art. I hope that the next 3 minutes may re-energize you so we can meet again next year with the same enthusiasm. forever trust who we are, and nothing else matters. Let's go for next year, 2023. See you next year, guys. Thank you.